we might, it's hard for me to prepare this because normally I know who the students are. This time I had no clue, completely no, I was clueless about what were that you were doing. So it's extremely, extremely hard for, but in any case, I am trying to get, okay. So let me start with Google because, okay, let me wait till you start. We need to get Miriam and Miroslav and Anastasia. Are you okay? Huh? Yes, Miroslav? Okay? Okay, so let's start. Again, ask questions if you wish. Okay. So I think we should start with Google Earth Engine because Google Earth Engine, first of all, most of you know it, and second, you might. It set a certain paradigm by which big data analysis was formed, and the deal here is that Google Earth Engine. What did it provide you? It did very interesting things, which is the first place where you would find the data. So the logic of Google was very interesting. Okay, I'm going to give you the data, all the data that I can find which is open. I'm going to give you an interface by which you can code in a very nice API by Google in which you can do things. And I'm going to give it away so that anyone can use it. Now, of course, they're having second thoughts about it, but never mind. And if you actually ever looked at the original Google Engine paper by Noah Gorelick at Remote Sensing of Environment, you, of course, no one has looked at it, but there is a section called Acknowledgements, in which he acknowledges there was a workshop in Googleplex where some people came there and gave a lot of ideas of what became Google Earth Engine. And yours truly was there and was one of the people credited by giving the original idea to Google. But of course, the implementation is theirs. Now, what is the other side of it? The other side of it is, of course, Google being Google. They were not allowed to do whatever they wanted. They had to fit into the Google model. The Google model is basically optimizing queries in hard, very, very, let's say, trivially parallel way. If you ever heard about how Google does things, it picks a query like Vienna Center or big data from space and sends this query to thousands of services which are completely distributed. And then they respond to these queries, and then they have another algorithm which kind of ranks this and presents to you the important bits. It used to be perfect because they had a very nice, they call this map from the sense of the mathematical, the astrophysics know this, a mapping in space, and then a reduce, which is putting things together. And now, of course, you get, first, before you get the real thing, you get advertising, advertisement. That's another story. But, so, this was what Google had to work with. And they said, okay, you can do anything, but you have to use the Google distributed system. So they devised a system which picked up the image and chopped the image. Every image that comes into Google is chopped in very small bits. And each small bit is sent to one machine. So that when you present your algorithm to the machine, it actually, or you write NDVI, it actually, oops, I think you might want to sit somewhere else. Oh, unless someone fixes it. But it's going, no, sit somewhere else. Come on, why do you have to sit there? Sit here, sit here or there. I mean, come on, this is going to constrain you. So sit in a better place.
Okay, thanks. Yeah.
Okay, so what happens? What happens is that the algorithm is then sent to each machine and processed in parallel and gets back. Is life, what's happening here? I think you're trying to do the wrong thing.
Doesn't even take me in.
No. I mean, you're trying to do the wrong thing, right? No. Sit somewhere.
I can use it by now. It's all right, thank you. Sorry for this.
Okay. So which means that when they designed it, they designed a system which is very good to do NDVI, or very good to do any kind of operation which is trivially parallel. For example, any pixel-based filtering classification. Now, anything which is not trivially parallel, it's very hard to do because of the architecture. That does not mean that you cannot do it. That means that it's hard to do. The other point is, of course, that Google Earth Engine is the basics of Google Earth Engine. The API is proprietary, and then you can only do what they help you to do. For example, if you ever tried, I don't know if you ever tried to run a deep learning algorithm on Google, and the fact is you can't. You have to export this to Google Colab and then start paying some money for it. Okay, so that's one of the issues. Never mind, but I think we have to keep in mind some lessons that came with Google Earth Engine. And the first lesson is, if you write a nice API, people will use it. It has to be simple to learn. We're going to see if people have done this. Okay. The other point, which again is probably the point that attracted you to this lecture today, was a point about time series. So what's the deal with time series? Well, the deal with time series, let me just see if I have, okay. The deal with time series is mostly clear when we are starting to deal with change. There is a nice paper published in Ambio which called "When is a Forest Not a Forest?" So I'm going to go slowly, maybe if I'm getting too slow, you please tell me. I need some feedback. I only work with feedback because I have a lot of things in my mind. And like any crazy scientist, sometimes I get confused in telling you what you should do. So you don't have a normal person in front of you, you have a crazy scientist that lots of things in his mind. And if you don't ask him any questions, he's going to tell you crazy things about what he's doing. So please push me down, okay? But it comes with age. Chadson. Okay. Shaston. Okay. Okay. Very good. So this is a very interesting paper that any of you who are interested in time series should read. It's called "When is a Forest? When is a Forest a Forest?" A deceiving question who actually has a very, very nice turn to it. I'm not going to force this out of the point, but it's extremely well-written paper, which first of all says a forest is whatever you want it to be. In other words, different users have different perspectives what a forest is. And I would argue the same for similar kinds of ecosystems. But one of the points that she makes is that some of the definitions of forest actually, so let me go back to my, some of the definition of forest, they actually abstract the temporal feature. So here what you would have is you have essentially what would, if you had time on your side, be able to tell you about a forest. So again, the forest here would be measured by two things. One is time, the other one is the structural complexity. And let's suppose I have a measure of structural complexity, just for argument's sake. And the measure is such that distinguishes natural forest from planted forest. But let's look at one here. You say, okay, so there is a trajectory in time of a natural forest. And then when it actually comes back, for example, someone cuts the forest. So think of trajectory number 2 here. What actually happens is this, bingo, this is completely lost. So the structural complexity is lost. It existed before, it is lost now. And now another type of trajectory may be that there is a disturbance, maybe a fire, maybe someone cuts part of the forest, but then the forest regenerates. So it's a different kind of trajectory. And then the question becomes, what is the information that you are losing or gaining on the positive side if you understand what the temporal trajectories are? So think of the following. This is a real data set of a point in Brazil where you have an NDVI here. So from 2020 to 2022, you see a high signal here, which is characteristic of a forest. But then, at a certain point, this signal drops. And here you can see a typical signal of deforestation. So, and then the signal starts building up again over the years in a way which actually has a peak on a certain time of the year and then a trough, peak, trough, but the peak is not too steep. It's like a slow, like a very nice hillside. Well, this is the typical peak of a herbaceous pasture. And you see differences between time on the herbaceous pasture because it has to do with seasons, different quantities of rain, because the pasture is, anyone who knows a little bit about herbaceous knows that it responds very quickly and very rapidly to rain. And if dry years, it will be a little bit less. But typically, this is a pasture signal. And then it is actually replaced in 2013 by a very different kind of signal, which is this very steep curve, and then boom, down. And then a second year, there are two steep curves, which actually mean that it started with one steep curve, which is one crop per year, and then again started two steep curves, which is typically when you have two crops per year. So essentially, the time series give you the change which you don't get when you don't have time. So in other words, the logic here, when you have time series like this, is simple, and it's in Portuguese because I have another, but I'll translate. I mean, those who are from Romania can actually guess the translation, or Italians, or which means use all the data. So what's, in the end, what's the logic? The logic is very simple. You have a data set of Sentinel-2 or Sentinel-1 or Sentinel-3. If the data set is there, okay, what's the logic thing to do? Use all the data. Yet, back to Google. Does Google let you use all the data? Yes or no?
I would opt for no.
Huh?
I would opt for no.
You know, but you're not a Google user, but you got the right response. But you're a logical person. Why not? Then the question is, why not? No. It's not out. Google has money. That's not the question.
It's the computational time?
Huh?
The computational time?
Well, it's the computational time because of the organization of the data. I mean, it's not necessarily computation. Google has so many computers. But you know, it's the way, since you organize data for trivially parallel, spatial parallel tasks, and where a bit of an image is on a machine. And when you have time series, you want this bit here, and the same bit in the next one, and the same bit in the next one, and the same bit in the next one, which happens to be in different computers. In which case, it's not going to be effective, and you're going to waste a lot of time to do a trivially time. If they had organized the other way, time series would be easy, but you cannot win everything. So, in that sense, Google does not let you all the data. Anyone that has used Google Earth Engine knows of operations called reduce, in which you say, give me the best image of the year. Have you used it, and have you used this? Best image of the year, best image of the semester, best image of this period, right? In which it sort of compresses all the data and cleans and say, okay, this has cloud, this doesn't have cloud, so this goes, this is cloud. So it brings you an image. And what happens? What happens when you do this?
You lose some data.
You lose some data, and you lose a very important thing called
Time series.
time. No, you have time. You don't know, at the moment you have the best image of the year, what happens to the pixels? You don't know the date of this pixel. And you don't know if the date of this pixel is the same date as the next pixel. Because they might come from different images since you're just collapsing. Therein lies your problem. So that's why the whole business, and again, let me show you a nice example. This is a real example, by the way. So this is, we're going to use this in the course, if we have time and I don't speak too much. So the deal is the following. What is this? This is an area in Brazil where they have built a very stupid dam. It was completely, was a completely natural disaster. The dam sits more or less here, okay? You can see. And they took the river and they dammed it. And they make a completely foolish calculation of the digital terrain model. because you're supposed to build a dam and very carefully calculate the digital terrain model so it fills the model. And if you have a very shallow area, this is what happens. You have a natural disaster. You flood areas which you destroy biodiversity and in the dry season, everything here appears. Now, if you are, of course, for example, a crazy algorithm that has no time, and you look at this pixel here, and you happen to get an image of the dry season, you say, okay, this area has been deforested this year because it has no trees. It used to have trees. But in fact, it's a wetland, which means that you're fooled because you don't have the information. So the change, let me just do the following. I have the same. This is the problem. I didn't know who was coming here, and I got fooled by. Come on, just a point. I give so many presentations per year that sometimes I. No, yes, I mean people. Okay, no. Okay, back to English. Good. Okay, so what's the deal here? The deal is the following. If there are two ways of doing this kind of processing, and I refer to them, there are more than two, but in general there are two ways of measuring change. The first is what I called a space first, time later. This is, for example, does anyone know Global Forest Watch? Okay. How many? Just show. Okay, not bad. So Global Forest Watch is done by Maryland and a guy called Matt Hansen, good friend of mine. And Matt comes and he does space first, time later. If you see his maps, change in world, and he processes Landsat, for example, for 1 year. He has a Landsat processor there. And then he looks at the same, Landsat data, say 10 years down the line or 5 years down the line. And you go to his website and you see change from 2020 or 2000 to 2020 or 2010. And he does it that he gets an image per year. And he does some tricks because he say, okay, I'm not only getting, so that he doesn't have to face me sometimes. He says, no, but I take some indicators. We go back to the indicators later. So I take some indicators, the reason between the dry season and the wet season. He puts some gadgets in the data, but still is a time first, space first, time later. You compare things in time. Well, the alternative is what I call time first, space later. Time first, space later is that you would classify time series and then join results to get maps. In other words, time first means that you take a time series, you classify the time series, and after you classify the time series, you look at the neighbors. Then looking at the neighbors, you take some averages, some things that you would do. And at that point, you would say, okay, I first take the temporal information, then after the temporal information, I take the spatial information. I'm not claiming that this is better. I'm just saying it's different. It's up to you on your application to find out if it is. In my case, and I have a very specific use cases that I work with, deforestation, land use change, and the tropics, and that's what's my area of expertise. Time series beats anything. But it might be that in your specific case, that might not be the situation. But in any case, what's the trick to get if you want to do the time series? So you need to have an architecture that gives you the time series. You cannot say, then that's the Google lesson, okay? If you build your architecture, your data architecture wrong, it's very hard to deal with time series. So your data architecture has to be so that enables you to recover the time series and do the processing. And that's how this business of data cubes comes in. Who has heard of data cubes here? Everybody. Okay, so that's our first lesson. We're going to discuss data cubes. Okay, but I'm going to give you, don't worry taking pictures. Just send me an email and I'll send you the Dropbox to all my slides. And I mean, they're all for teaching anyway. Okay, so the basic story starts by building an architecture that enables time series analysis. If you don't have the architecture, you don't have time series analysis. Simple as that. And then when you have the time series, you do your change. But you need your architecture. And again, this is not today's tutorial is not about the software sets, but the software is going to be used to illustrate some of the ideas we're talking about, okay? So I'm going to jump a little bit this and give you another example of time series. Okay. This is a very tough one. I don't know how many of you have actually worked in tropical landscapes. Anyone? Good. Lorena. So how is it like working with tropical landscapes? Cloudy? Another thing which is also tough is, okay, one of the typical tropical landscapes is the savanna. Savanna, very rich landscape. Effectively, you have savannas in Africa and in Brazil. And do you know why there's elephants in Africa and there are no elephants in Brazil? Any guesses? Why there are lions in Africa and savannas and there are no lions in Brazil? Just a curiosity. Any guesses? A good ecological reason for that. Why there are lions, I mean, the savannas in Brazil are very similar to the savannas in Africa and Chaco. And why there are lions in Africa and no lions in Brazil? Because man, human, Homo erectus, emerged in Africa. Homo erectus emerged in Africa. And of course, very soon the lions, the elephants, the giraffes learned that humans are very tricky to eat them. And they decided that this kind of species was better be attacked. So hippopotamus, rhinoceros, they're not, kind to humans. And of course, humans have to be very, defending against them. Remember, I mean, the dates vary, but humans was born in Africa 1 million years ago. Well, human erectus, Homo sapiens, but take it or leave it. I mean, 1 million years is good enough. And when did they come to America? I mean, again, the dispute is on, but certainly less than 40,000 years ago, and the occupation of the savannas is 15,000 years ago. Well, 15,000 years ago, there were lots of big animals in the Brazilian savannas. They had there, similar to the African ones. But they were tame. So when these guys came, Homo sapiens, they had no idea of the danger it became. So Homo sapiens killed all of them. There's lots of big animals whose fossils are preserved in the savannas. So don't misplace the power of humans to destroy. We're doing worse now, but it used to be the case. So this is a natural savanna which has no elephants. It's in Brazilian Cerrado, but looks like it could be a Tanzania. Okay. This is a similar area, same latitude, and that's pasture. And you say, well, it's the same thing. No, it's not. The pasture here, from the biodiversity point of view, is an exogenous species. It's actually brought from Africa, Brachiaria. And of course, the cattle come from, anyone knows? Or they're native? Where do the cattle come from? One place on earth, India. India, which they used to be preserved. So, but in Brazil, of course, people like the asado or churrasco. That's another story. Now, from the point of view of biodiversity, it's very important to distinguish what is natural, what is man-made. Okay, so far so good, yet. And then you look at the ESA, which is hosting us. They paid a world cover 10-meter data. Don't know if anyone was involved. So it's done with Sentinel-2. What do they call this? Well, huh?
They consider it the same.
Yes, you bet. Very good. They considered, ESA world cover considers all these areas as grasslands. Okay? It's a sure way to be right and a sure way to be relevant. Because from the biodiversity point of view, from the protection point of view, from the greenhouse gas point of view, you should not call natural vegetation grasslands and pasture grasslands, and you're making a huge disservice to the protection of the environment if you do so. And this is basically my PhD student in his work would use time series very clearly to distinguish what is natural, which is the green stuff, and what is actually pasture, which is the yellowish stuff. The same area, same date. So, like I said, it's hard to beat when you have, of course, they took one sentinel image per tile, per sentinel. So they had to do something easy with space. It's not a bad product. It's just for us irrelevant. Because I cannot, if I'm a government official dealing with biodiversity, it has no value to me because it provides no information on biodiversity. So I cannot do anything with it. Okay, which means that to finish this part here, what are we going to look for? We are going to try to tell you today about a certain amount of things which are involved in extracting information from big Earth data. So we're going to take it step by step, but let's look at all the steps and then try to figure out each one. Okay, there's a lot of jargon here, so you have to be clear on the jargon, otherwise you lose the context. So the first thing here, let's look at the other side, obtain and harmonize ARD. Who has heard of ARD and can tell me what ARD are? Look at that.
Analysis-ready data, which means it's data that is already pre-processed and condensed in a way that we can easily test.
Is it analysis ready?
That's debatable, but that's what it
Okay. I'm going to argue later that analysis-ready data, in fact, not analysis-ready. So the first thing we're going to do is describe what analysis-ready claims to be, and it's not. And then now we have cloud collections with analysis-ready data. Okay, Google Earth Engine is one of them. Microsoft Planetary Computer is another one. Earth on AWS is a third one. Digital Earth Africa is another one. The Swiss Data Cube is another one. The new Copernicus system is going to be another one. They're cloud collections. Essentially, they're cloud collections of analysis-ready data. Then, remember that I told you that we need a data cube. A data cube is an organization of the data that allows you to extract time series. Remember, the organization of the data is key for the extraction of the data. Okay? This is one side. On the other side, if we do machine learning, it's only as good as the training data we have. And therefore, we need to collect data sets. We need to do some quality control. We need to use training data sets. So after we have the right side and the left side okay, then we can classify the data, and then in this case we're going to classify with space first, time later. Okay, enough of slides. Let's go back to Kaggle. And where is I? Or okay, so let's keep this. Well, let's start with this introduction. I hope it works. And I need to make this big. Okay. So, there is, I'm not going to go too much on sits. We're going to look at the data first, and then you have to click Edit in your notebook. Okay, so I hope that you all have gotten to this point. Have you? Yes. Okay. And there is a, well, first part of this notebook, there is a description of how sits work. We're going to skip this. I'm just going to tell you that if it ever looks similar to Google Earth Engine, it's not by accident. We look at Google Earth Engine and try to develop an API which was as easy to use as the Google Earth Engine. But the judgment is here. Oops. Okay. So let's run this. So the first part here is installing what we call the bundle. The bundle in Kaggle is lots of data, which essentially there's a library with the software and there's a library with the data, which is the examples. So you should run this bang and says session started, and then it turns until it finishes. And let's see. Whoops. I hope it works. Sometimes it takes a little bit of time because, okay, what? Okay, it runs, and then after it runs, you can load the library. Okay, don't worry too much about the syntax. If you have doubts, tell me, but essentially, you should get this result here. This is SITS12421, which is the latest version which is available on CRUN. And the documentation, like I said, if you really want to learn SITS, which is not the purpose of this tutorial today, given that you are Python people, there's a book. Huge book, lots of things here. So if you ever want to really learn a good language, you should learn SITS with R first. No, I have nothing. I like Python. Like I said, I like Python. But the problem with Python is it's very easy to do a one-person project with Python. It's very hard to do a community project with Python. Okay, but let's go. The first thing here is we're going not, it says creating a data cube, but in fact it's actually picking up some data which is already being organized. This, of course, this being the first example of an introduction, this has already a set of data which is already organized as a data cube. So in case you have doubts about what it is, it's essentially, well, a set of data which is its data, and then mixed data synop. So this is this. Oops. Essentially, essentially is a set of files. Okay? It's only that they have been nicely organized as a data cube. In other words, they fit a certain area, they are periodic in time, and they match. So you have the same area, and you have the dates. But let's look, and we're going to show how to build such a cube in the first lesson. So what is saying here, I'm taking a lot of files, which are on my directory, and I'm creating a cube out of them. And this sparse info here is just to say what is the name of the files. If you go back here, you see that it says Terra Modis 01 012 010, which is the Modis style. Cloud is the band, and this is the date, 1st of November of 2013. So run. Oh, why is that? Oh, I'm sorry. It should be this. If you type question mark sits cube, you actually get the whole documentation of the function doing everything. It gets a long, long story. Let's not go here. Okay. But let's see what are the bands that they are on. So let's go to sits bands, and it should tell you that it has 3 bands, cloud band, EVI, and NDVI. Okay. Let's plot a color composite. So click on plot synop. Basically, it's going to give you a plot. And there's some message here because they're changing. Again, I know that some of you that have worked with packages, this is the package maintainers from this package are telling you something. Okay, so this is an area, and this is the coordinates a little bit small because of the size. Let me see. We can change that. Let's do the following. Options. We can do the following. Let me just remember. Let me remember myself what I have to do here. Sometimes I forget what I have done. Okay, this is it. Kaggle has some very, so if you type, let's do this, 12, 7.5. Okay, let's run this again. So I just changed the width and the height. Okay, a little bit better, but not too much because it's too big for the screen. So, oops. So I should put 10. 10 is 6.5. I'm sorry. Just because I've changed the size of the screen, then it gets all messy. But it should work on your machine. So you just 10, 6.5 should be okay. Go. Come on. Oh, why is not? Why? Oh, come on. Something strange. It didn't show it here. Oh, it does. And then it stopped. Well, it's probably the network is lots of people using now, but I hope you get on your screen because, okay, it's here. Okay, and you should get normally the nice coordinates here. And because I'm blowing up the screen, the things in Kaggle is not good for graphics, so it gets a little bit strange here. But you should get the coordinates and anything. And you can now go, for example, and plot the NDVI and plotting a false color image. Okay, now that's better. Oh, that's nicer. So this is basically the NDVI in a color-coded way. Those of you of cartography, are those, anyone from cartography has heard of the brewer, color brewer? No? Does everybody here do maps? Have you heard of color brewer? No? Oh, come on. Color brewer. You should know about the color brewer. Now you know. Why didn't you tell you knew? The color brewer is actually a professor. It's called Cynthia Brewer, has her name, and then she basically is some advice of how should you color your maps. So sequential, diverging, and these let me see if I can make this bigger again. Okay, you can see 3 class, let's say like 6 class. You see green, blue here, G and BU. And then you get like yellow, green, blue, yellow, orange, brown, yellow, orange, red. Okay? And if you go back to Kaggle, what's written here? Oh, it's written nothing. Haha. But because at the default is palette, I think it's yellow, orange, red. I think it's this is what I put as default. I hope. No, it's not yellow, orange, red. It's yellow, orange, green. Sorry. Plot. I had a default which looks nice, and so plot time series in package sets, and there should be a default somewhere. Plot raster cube. Red, red, yellow, green. Yeah, I knew there was something. So palette, red, yellow, green. It's very nice to use these palettes because they, okay, that's the one, looks nice. So this is basically color brewer. So if you do maps, at least if you hadn't learned anything today, you can at least remember Gilberto told you about the color brewer. And next time you do a map, you use a color brewer. I mean, these are, seriously, these are very much tested palettes that should be good. But again, do you have this in Python? No. No, but you have this in R. You know, you cannot just say, okay. No, for graphics, I mean, for graphics, there's no competition.
Matplotlib does have very extensive color maps, but they're a hassle to get around.
Yeah, but you see, but do you have all these niceties that plotting, the coordinate systems, everything? Okay.
At least for astronomy, there is.
No, I mean, I'm talking cartography.
And just like in Python, it's really hard to have all these nice axes and things like this. Is this based in base plotting? Or
No. This is, like I said, this is I was just trying to convince you that there is 2 worlds. One that you do things by yourself, and another that you rely on things by others. And in this case, for example, if you see SITS, it's about 20 packages rely on. And one of these is TMap. Where is TMap? Torshop, TMap. So TMap is a very nice package to build thematic maps. And there's also, if you do spatial things, there is unbeatable called SF. I mean, GeoPandas doesn't even come close. There's no comparison. You simply cannot do the same things. It's much better by thousands of miles. And Pandas doesn't match the the tidyverse. I know why people like Python, but they cannot understand it, but never try. Okay, fair enough for my rant. Okay, so now you see this is, okay, what have we just seen? We have just seen one date of the image. And you say, oh, what about the other dates? So if you go back to up here and do timeline, SIDS timeline of SINOP, and run. Just like that. Okay? Just type SIDS timeline, oops, SINOP, SINOP, it's the place. Then you get this. So what I'm having here, I have a data cube that covers a certain area. And by the way, if I just say, okay, what is this data cube? Ah, good question. What is a SINOP? Aha. Aha. And there's whatever, bit of the cube, file info, and then there is a, so it says it's a satellite, a sensor, a tile, IMAX, and then the problem is the CRS nowadays is this very crazy, this is, sorry, but you have to, don't complain to me, complain to the Open Geospatial OGC who established this kind of long-winded way to express a CRS. And I'm not the culprit, it's the guys who standardized it. And then if you type a SINOP file, info of brackets, brackets, 1 brackets, brackets, you get, it's a little bit, again, confused because of the CRS. Okay, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One to 10. No. 1 to 10. Just, okay. I take the CRS out so I can see better. So this is the information about each of the files which make up the cube. So the files are there. They have not, I mean, I just said, well, since these files are nicely organized to make a cube, I'm going to put this information together. So this is meta. Yes, go ahead, Miroslav.
So these are information about each of TIFF file that we saw at the beginning?
Yes.
So each TIFF has one band?
Yeah, let me show you the file. So let's, okay. So imagine, very, very good question. So let's type like this. Can you, okay. Okay, so I just did list files and I copied this bar here to here, okay? It's a strange R story, but system file package, it's because you can load data inside packages. So it sits data as a package with data. And one of these data sets is the SINOP data set. So if we list the contents of that data set, you get this. These are Terra, MODIS, so satellite, sensor, tile, band, date. Satellite, sensor, tile, band, date.
In one band.
One band. Because that's what you get. You see, that's the, why is that organized like this? Because that's what you get when you go to ESA, when you go to Google, not Google no, but when you go to AWS, when you go to Microsoft Planetary Computing, when you go to any service, you get, essentially what I'm after is when you do a stack query, if you know what's, how many of you know stack? One? Okay, we need to do, okay. So when you do a stack query, you get bin by, you get file by file. So this is what it is.
But how does it work with real-time series data, like with
We're gonna show.
Grips or net-
Which one?
with grips or netcdf.
No. No, wait. There's two things here. You have to, the current situation is that when you get a stack, it's a long story, but let's shorten it. Currently, what is available in the data sets that we are talking about, which is like Sentinel-1, Sentinel-2, Landsat, Sentinel-3, and so on, are files which are the TIFF or JPEG 2000. Okay? And that's what it is. And then when you get netcdf files, that's another story. And then you need another pack. The problem is they don't work well with stack. You see, this is something that.
I'm just wondering if this is.
No. Because again, you remember that you have, when you develop a software, you do it in stages, and you have certain objectives. And in this case, we had an earlier objective of dealing with land data, Sentinel, Landsat, and so on, MODIS, in which the requirements are this. If you do ERA 5, it's another beast that we have not touched. Because, again, there is only so much that you can do in terms of software development, and you have to have very clear aims. And you have to know what your users need. So that's the point.
Yeah.
That doesn't mean that we're not going to do it in the long run, but we need users. Without users, we don't move. Okay, so back to the point. We're almost breaking for coffee in 10 minutes, so let's finish this. So what I'm saying is there is a set of files. Let's go back. If you understand this, I think it's going to be easier later. There's a set of files. We'll get later to do how they came to that point. These files can be built into a data cube, in which case I collect that information, organize it nicely in data metadata here, rows, column, resolution, what heck you, projection, and so on. If I collect everything, I'm able to trace the timeline of that database because I know where it starts, where it ends. And I'm also able, simple thing, to plot. So let's take, for example, the next image here. Instead of 2013 0914, let's take the next one in the data cube and plot it. It's a different. So it's a different NDVI for different date. Of course, the colors look different because the image has changed, and then so on and so forth. That's one way of looking. That's looking space. Now, let's look at the time series. In this case, there are two ways, but essentially one needs to organize time series in a certain way. Those of you who are familiar, how many of you are familiar with PostGIS or simple feature on Python and so on? Okay, so if you, okay, so here, these are time series. In this case, they are samples. So they look very much like a PostGIS or a simple feature starting here, in which they have attributes like latitude, longitude, start date, end date, label, and cube. And then there is another column called time series. So if I now do, I don't need this. Let me erase this. So if I now do samples Mato Grosso 1, let me get the first element of these samples. Let me get the time series. Let me get it. And then run this. Okay, so what am I looking at? I'm looking at this first element, minus 57.8, minus 9.76, which has a starting date at 14th of September of 2006 and an end date of 29 of August of 2007. It is was labeled as a pasture, and the time series has 23 elements with 5 columns. And what are these 5 columns? Well, they are the date, the NDVI, the EVI, the near, the mir, or what have you. And here's the time series. Okay? Dates, values. Any doubts? Yes.
Does that read from a pixel or?
This is taken from a pixel.
Yes,
So this is, huh?
It's not some kind of resampling.
No. Again, what happened here was the analyst went into QGIS or whatever system. It looked at the time series, looked at the images, and then said, okay, in this point, there is a certain pixel, okay? And this pixel is pasture. Or, to be more precise, this pixel was pasture starting from, in this period, 14th of September 2006, from 28th of August of 2007, this was a pasture. To be more precise, time is of essence here. So you say, okay, this was a pasture during this period. Not necessarily that it is a pasture now. So when it was a pasture, and I'm saying this for this year, it had the following values of NDVI, of EVI, of near infrared, and middle infrared. So remember, now time is clicking. So now we have time as something which is very important here. And I had, for this data set, a number of classes. So let me then, for example, let me run this. Configure graphics output. So let me start with the following code. Sits of summary, samples. Oops, too much. So what do I have? Normally, summary is a generic function in R. Oops, I'm sorry. Okay. Which tells you things about the data. It tells me that I have 379 points labeled as Cerrado, 131 as forest, 344 as pasture, 346 as soy corn, 352 soy cotton, 87 as soy fallow, and 180 as soy millet. Okay, so it means that someone actually collected there or went to the field or something. And now, look at this. If you say sits view, and you get something nice here. Oops, got the wrong continent. Sets, view, and then the samples. What do you see? You see something very interesting. What can you tell me about that data? What can you tell me about the data? The colors, of course, correspond to the labels. And, of course, the points, the bullets, the small. The guy went, you know, there's a road here. He picked up a Mitsubishi, whatever, and he started looking around and said, what do you have here? I have this. Okay, where? And then took the, yes. And if you do similar things to your data sets, you're going to get a lot of surprises. What it means in practice is our training data has biases. And there's no, but it's always nice to visualize, to understand what these, what these things are. And there are even better ways. But you see, there's, don't trust too much your training data. But to finish, let's just do this one. So I have, remember, what do I have now? I have lots of training data, right? And I remember I have labels, Cerrado, Forest, Pasture, and I have bands. I have labels and bands. Now, you can ask yourself, what is the variation of this data? How does this data vary in time? What can you tell me about it? Okay, I want to see, I want to visualize that. Here I just visualize the location, right? But I want to visualize more. I want to see, and then I want to see the distribution. So I'm going to do, just to simplify things, 2 cuts on your data. The first cut is selecting just one label, forest. And the second cut is selecting just one band, NDVI. I could plot everything, but it's just a little bit of time. So samples forest using a function called filter depler. Don't worry about it, it's R thing, but essentially is a function that picks up out of all my samples those who have a label forest. Okay? And then the second one is selects from the data, from the first one, only the forest, the band NDVI. And then it plots. So let's do it. Bang, you have it. So what do you get? What can you tell me?
Answers of all the points, trend and confidence.
Yeah, I mean, first of all, there's a mess. Within the mess, there's some logic. There's logic in the madness, as Shakespeare would say. Okay, and the logic in the madness is explained by 2 things. The dark brown is the median, not the average. In this case of this data, never use averages. Always use medians. Never use standard deviation. Use interquartile distances. So first, basically, it is the standard, the median, the first interquartile range, and the third interquartile range, which is much more robust measures of distribution. Which means that despite the little bit of noise, which is inevitable, the data is, well, quite well behaved. In other words, NDVI is good to consistent indicator of forest. And I think this is a good point for us to have a coffee. It's 10:30. If you want to spare 30 seconds, tell me how are you doing so far, whether you're bored, you're interested, and it's worth your time here. I'll be, any comments?
I'm enjoying something new for me, at least.
You're a gentleman, huh?
Interesting so far.
Yeah.
I like it.
Finally learning something.
Huh?
Finally, I'm learning something.
Okay. I mean, you're welcome to leave at any time. I've not, I mean, this is like, my interest is to learn something, and I'm really not interested in teaching SITs to you. I'm using SITs as the example. So let's break for half an hour, and we come back here at 11. Whilst the others are coming, I'm going to spend 5 minutes just reviewing the key stories that we passed on. And the key stories are, in the end, about simple, which are the following. And I hope that you can agree with me. If you want to work with time series, you need to organize your data such that it helps you. Data architecture should help you doing what you stuff. And in this case, you need images. For example, this I'm showing you some set of images which I will call make up a data cube. They're from a satellite, they're from the same sensor, they cover the same area and different bands, and for each time you have all the bands that you are interested in. In other words, there are no gaps. You need this data structure, which consists of course, your data nicely organized and some shell on top of it, the metadata, which says, okay, this is my data set, this is how it's organized, which data there is, how many rows, what's the projection, what are the geographical coordinates, what are the time for each image. You don't need to use what I've used here. You need to use something similar that conveys the information to you. Okay? I'm going to call this a data cube. So, the next thing you do is, of course, to be able to run machine learning, you need some structure that assigns for places on Earth labels in time, in space-time, as we'd say. A place on Earth, latitude, longitude, a start date, an end date, so it's located in space-time. In this case, a label. And some way, again, you don't need to use this structure. You need a structure which conveys your information in such a way that you can use it. And in this case, for example, that you can, for example, ask how many data points do I have? Where are they? Oops. In space. Where, for example, how do they vary in time per band and per class? This case here, the last thing we showed was for the whole data set we had for one class, forest, one band and DVI, all the samples, which are in blue, the median of each time step, the first interquartile distance of each time step, the third interquartile distance, gives you an idea of the spread of the data. So, the first part of our class was an introduction to architectural issues or data structure issues, as we might say. So if you want to use time series, you need proper data structures. You need to organize your data structure in such a way that you can do something with it. Some questions, any points? Any questions? No. Okay. So now that you have the two things, we can look back to our famous diagram here and see, for the moment, I have a data cube. Then we're going to learn a little bit more about this. And for the moment, I have a training data set. Why training? Okay, oops. Okay, so I have both sides of the coin. Now it's time to join them. In which case, oops, you join them by training a machine learning model. Now, the first thing you have to do is to make sure that your data matches, the cube. So here you have the samples. They cover 23 dates, which is actually corresponds to one MODIS year. For those of you who ever used MODIS knows data comes in 16-day intervals, and therefore you have 23 images per year. In this case, it's not, it's, why would the stupid guy start in September and end in August? Why would anyone be so damn stupid to do this? Or is there a reason? Yes? Is there any reason why I don't start in January and in December? Huh? Well, it's the season, yes. It's because in this case, those who did this work are interested in agriculture, and they want to capture the agricultural year, which in this case, for this region, starts in August, starts in September and ends in August. In other words, you can choose whatever time you want, as long as your data is compatible. So now I have 23 data sets. And by the way, do I have 23 timelines for my cube? You can count, but I'm going to tell you that you have 23 timelines. Okay? Did you get it? I'm not going to count, but it's 23. Otherwise, it would not work. If you have a 23 samples time series and your cube does not match 23 samples, how on earth are you going to match the two? So you need that your data set, training data, in terms of timeline, matches the timeline of your cube. But, notice one thing. This cube starts in 14th of September of 2013. It ends on 28th of August 2014. What about the data set? Well, at least this first sample does not start in 2013. It starts in 2006 and goes up to 2007, although the very same dates, 23 dates. Is that a problem? Is that wrong? Did we make a mistake? The date should be the same. Should they? Everybody agrees.
These values could be different on a different day.
I'm sorry, could you?
So for a particular point, you know the classification.
Right.
And you know the NDVI
EVI and so on. But
Yes.
on another day, you can have other values.
Yeah, but this is very interesting. What you are saying, well, again, there are two ways to say it. In principle, if you want to be completely sure, you would just use exactly the same dates, 2013, 2014. You can, there's nothing that prevents you that said, there's an average behavior of pasture, which is about the same come year, next year, the other year. So in principle, I could collect data from a certain year as long as I take the same period, say the agricultural calendar. And the curve that the pasture makes should be similar. Remember that example here?
Yes, but for instance, in 1 year, I didn't plant something on that particular field, and I get different results, no?
Wait. Very good point. Very good point.
If I know that the result...
Wait. Remember that there's a starting date and a label. Now, by definition, training data needs labels. Okay, so you cannot classify. So what I'm saying is this data was pasture in this date. Now, the hidden assumption here, what's the hidden assumption? The hidden assumption here is this. That more or less, I think if I... Better? Okay. That if I'm taking these classes here, the signatures of pasture are substantially different from the signatures of agriculture and forest. And they are similar per year. So 2006, 8, 9, they're more or less similar. So sometimes I happen to have been to the field many times, the same place many times during different years, instead of going to lots of places. It's an inevitable condition of getting data. Sometimes you don't choose. Sometimes data is given to you. So you have to think a little bit and verify. In this case, the assumption is the signature of this class is similar year after year enough that it can distinguish this class from the others.
Yes, but you said that you have just 23 files.
23 time steps, not 23. I have 23 files. Wait, I have two.
Images of different dates.
Yes,
No?
okay, let me get back. I said, I have 1 year worth of images. And I want to classify this year. But it starts in August, starts in September, ends in August. And I have 23 times 3. I have 23 clouds, 23 EVIs, 23 NDVIs, okay?
Yes, but if you have just 23 individual samples.
No, I don't have 23 individual samples. Each sample has 23 times. Look, sorry. I took here this is another thing. So this is, when I say 1 comma, means the first, this samples here has, if I do the following. Okay, let me get, okay, simple thing, and row. Oh, I think I have to start everything again. Gosh. Yes. I think you have to restart because Kaggle takes you out. What is it? No, yeah. I'm sorry. Apologies, but that's a Kaggle thing. We need to go back and run our commands again. Install. This is Kaggle, so it does not keep the session open. So it's now, if you have to run, you run it again. But what I was saying, you have something, I think, if I remember correctly, how many, something like, let's see, I'll see. In a moment, I'm going to show you. Okay, let me go step by step. Just a second. Okay, so I have the files. I have them, I show this. Timeline, I plotted. Okay, fine. Okay. Okay, labels. Okay, so 1,837. So I have 1,837 samples. Okay?
So yeah, I think it's the number of sample points, no? So if you sum the...
Now, the number of sample points is 1,837. Each point has 23 values of each band, NDVI, VI, near infrared, middle infrared. So what was your doubt then?
I thought that you have one value for each of these 23 images, and in this case you cannot see on the plot, on the slide, if you have the same distribution, you get just, I don't know, one.
No, but I don't have one value. I have, see, for example, how many plots are actually, how many plots have I plotted here? It's simple. Sorry, it just keeps getting on. I have 131 samples of forest. Let me take pasture, 344. So let me do differently. So let me take, instead of forest, let me put pasture here. And let's keep NDVI for the moment. Okay? So now I'm taking 300 out of the 1,800, 344 samples of pasture. Okay? Then out of the samples of, well, called forest, but it should be pasture. I took the NDVI, so I actually should write this. Samples, pasture. The amount's the same, but let's just do this nicely. Samples, pasture, samples, pasture. Okay.
You had to change samples for
Oh, samples pasture. You're right. Thank you so much. Okay, so back to your point. So now you have the pasture as it changes during the year, and there are I can tell you for a fact there are 344 blue lines. And then the red, the sort of brownish thing, is a median. For each 344, the time instance 1, what's the median? Okay. And then you go step by step and you get the median. The median is supposed to tell you what's the median value. And then the bounds are first interquartile, third interquartile. To show you how the spread is, it's not bad. I mean, of course, you can always improve on things, but it doesn't seem too bad to me. So again, so I'm still trying to understand your question.
No, it's okay, I understood now.
Okay. So back. So we have the condition. Time condition is all my training data has 23 time instances. The data condition, the cube, all the cube has 23 time instances. There's one other condition that has to be met, is the bands. The cube has only 2 bands, the data has 4 bands. So instead, in order to train, I need to match also this. So I'm going to select out of the 4 bands here, and DVI, VI, near, and mirror. These are 4 bands. But the cube has only 2 bands, so I need to take, always keeps this doing to me. I need to take, okay, 2 bands. And then I do my magic here. The nice magic is this, okay? How many of you know about random forest? Everybody. Very good. How much work do you have, how many lines do you have to write normally to train a random forest model?
I don't know.
Have you ever been able to write 1 line and train a random forest model?
No.
Well, you don't know now. That's 1 line. Sits train these samples with this model. If you want to do SVM, how do you think the system does it? Any guesses? If you know.
R4 to SVM?
You change R4 to SVM. How many systems you know that you can do this easily?
Classical machine learning models?
Yeah, no, I mean Pangeo, OpenEO, Google Earth Engine. None. Sorry, but none. I was looking at EOLearn the other day, and EOLearn, I mean, I don't want to pick with my synergized people, but there was scikit-learn. What is the example? Land use and land cover. Okay, so look at how many lines of code do you have to write on your favorite language. Okay, that's part 1. And then part 2. Prepare the training data, model construction and training. Look at how many lines of code you have to run a very simple, this is like, not a SVM, but I think it's linear, well, it's the very simple light GBM model. This is everything you have to write. Model fit, right? Okay.
So
No.
Is this function taking care of also splitting training and test data, or is
Yes, it does everything for you.
And what about the parameters, like the depth of the...
Okay.
that goes in the parentheses?
Okay. Now you have to wait a little bit.
Okay.
Don't jump. No, in fact, what happens is this open, close, you can put in, for example, entries or something like that. There's each behind the scenes, if you type sits this, okay? Behind the scenes, if you really want to do things, for example, here, you can have, for example, any parameters that you pass on to random forest. Or if you now go into, for example, temp CNN. Has anyone heard of temp CNN?
Yes, yes.
Yes, so temp CNN by my friend Charlotte Pelletier. I know Charlotte. Charlotte is a very good friend. Yes, you can write temp CNN, nothing, or you can write all the parameters. And if you really want to do it, okay, be my guest. If you really want to do it, you can go and do deep learning model tuning. So we have functions for model. Now, if you want to go to all the story, there's tuning parameters by which you can choose the learning rate, the weight, only if you want to. But if you want to, yes, there's tuning. But once you have your model tuned, if you just want to see things running, random forest is the easy one because it doesn't really make a difference. But in any case, let's go back here. So the idea, this is a package for end users, like Google, only better. Now, explain to me this. Okay, wait, run. Did I lose again the story? No. So, since everybody knows random forest, everybody can explain this to me. What is in the earth is happening? Yeah, okay. Let me make it a little bit bigger. Yes. There's someone who thinks of the users, right? Someone who likes you. Where is this stupid thing that I can get a bigger? Oh, come on. Options. This. Okay. Kaggle doesn't like me, so I don't like Kaggle. No, let's see. Here. Okay. Let's make this bigger. 12. 12 is what? 8.5. Or 7.5. Let's try. So since you know random forest, you can tell me what you think about this. So what's happening here? Let me make it very, sorry. Why? Doesn't like me. Oh, shucks. Oh. Let me try to do this. Oh, you cannot see it here. Let me try on another. It's the same thing. Here. Okay, see if I can have. Oops. This is the problem with graphics. View.
You can open directly the image and you can
I can open directly the image. That's. Can I?
Right here, open image and then
the first one.
Oh, thank you very much. Good. Now you can tell me what it is. What is this? Come on, everybody knows random forest, so you should be able to explain this to me. Huh?
feature important, like the.
Yeah, but exactly what are we talking about? Which is,
So like, it's not, because it has the number, I guess, for the timestamp that it's using, right?
yes.
The I for times like 9 and the I for times
Okay.
20.
So, yeah, you're right. You're on the right track. Continue.
Yeah, and that's it. Then the minimal depth, I do not know.
Okay, let's take the easy ones first. What is EVI 14?
14th step of EVI.
This is EVI for the 14th date, okay? Which happens to be, if you have to count to 14 there, the 14th place on the timeline. And here, 3.62, you remember random forest has trees, and that there's 100 trees. The question here, in which level of depth in the tree is the variable, and then is it at the first, second, the third, or fourth? On average, the EVI 14, which is, according to random forest, the best explanatory variable, is on depth 3.62. That's the one who explains the most. And then you have EVI 17th, EVI 16th, and EVI 21, and EVI. This is very in the end of the series, there's NDVI, and so on. These are the most explanatory variables in terms of trees. So basically, and here you can see, for example, in about, you can actually go here, in about 10 of the 100, it's 100 trees you can see here, in about 8 of the 100 trees, that's the first point. Minimal depth 0 means that it starts with EVI 14, right? And then boom, and then goes to, for example, EVI 64, and so on. And this is the good and bad of random forest. Because once it enters a branch of the tree, it doesn't go back. So it decides that you are here, and given that is EVI 14 bigger than a certain value or less than a certain value, then it goes in this way, and then up to the end, and in the end gives you a class, which tends to be very good at more frequent classes. When you have lots of classes, less frequent classes, get into trouble, because random forest cares about the average of the result. So if you have like a lot of areas of forest, a lot of areas of pasture, but you're interested in planted forest, and then random forest doesn't care about you. There's no agreement with him between the guy who did random forest and you. He's trying to get the average value, which is not. So random forest always produces an overall accuracy, which is the starting point. That's what I tell my students. The first thing you have to do with your data set is run a random forest, because you cannot do worse than that. There's no way you can do worse than that. You can try to do better, but there's no way you can do worse. So at least you can have something to present to your employee, to your teacher, to your paper. You know, you're safe. Now, that does not mean that's the best one. That only means that you have survived the task that you've been given, which is, of course, good enough for most purposes. So that's the model. It helps you understand what random forest does. Have you seen this plot before? Well, thank you very much. Okay, so now the last bit is we have a model, we have a data cube, then we run the classification. Now, one other funny thing. What should be the output of a machine learning classifier? Trivial question, or no, that's not a trivial question. What is the output of a machine learning classifier? Probabilities. Do you get this output in probabilities in Google Earth Engine? You don't. Thank you very much. Thank you very much. You should get, I'm not sure you get out on Pangeo, but it's another story. Okay, so what you actually have here, let me do, what is it? Let me do the trick, which I've just learned. Old people learn new tricks. Okay, so that's the forest. So what is it? What is shown here? It's on a scale from 0 to 1. The probability assigned to the class forest in this classification. Okay? And if I could plot the same thing for all the classes.
The impact of testing started in June 0.12. Please have to the room.
Okay. So what?
Miss Bernadette, Luke, Miss Iris, developer Casimir, Moates, Miriam,
What's that?
We remain here.
Okay, can we continue?
Thank you.
Okay, so now I can continue with my question. What can you do with these probabilities? The two things you can do. What can you do with the probabilities? Well, we can do a threshold, but remember that you have the output here if you have classes, okay? Remember that what we're talking about here is a classification. So here I have lots of labels. So I only put, but I could try pasture here, couldn't I? Oops. So I could have, remember that for each label, you have a probability map. Okay, fair enough. Okay, so that's different data because that's no longer the data for forest. These are the probabilities for another class, which is pasture. And so on. I could try, and then you can look at the data and ask, so you have, for example, soy corn. Soy corn means the guy planted soy and then corn. So like soy underscore corn. Okay, so you run. It says, again, it's been nice to you telling you that it's running again, but yeah, okay, it says I've done it. Okay, so you have a different probability, obviously. Now that you have the probabilities, what can you do? Yeah.
You just pick up the maximum?
You could just pick up the maximum. You are correct. That's the simplest thing to do. That's what Google does. Remember where we started. We started here. We started here. So, what actually can, now that we're talking about space first, time later, is that a certain way by which we could do something about space? Now we've classified, and that you can do using whatever software you have, each time series, a pixel classification. And up to now, we did not consider any space component. Now that we have the probabilities, can we do something about the problem? We have, for each class, one probability, 0 to 1, 8 classes. Can we do anything with it? I'm sorry? We can overlay them, yes, that's fine. I agree that you can do it. I said you can do two things. You got the first one. What's the second one?
Select the highest probability class.
No, that's the same. Overlay selecting the highest probability class. That's,
For example, we can make an analysis of each pixel, for example, have 50%.
aha, now we're getting
Maybe
somewhere.
It's another class that we don't have.
No, not necessarily another class. Well, there's,
Or
there,
where the
yes, yes. Remember that in the end, at the end of the day, at the end of the day, this is multivariate statistics. Okay? Therefore, I'm going to spare you the details, but one thing you can do if someone, has anyone worked with Bayesian smoothing? And, okay, the guy, tell us what a Bayesian smoothing is.
Well, I'm feeling put on the spot here.
Oh, come on. If you said you have, no, your best guess about it. Come on. There's a, go ahead.
So what I've used it for is to constrain the extent of globular clusters, given the radial extent against the distance axis.
Yeah, but you basically are taking spatial constraints into example. There's a general sense that we can call this is borrow strength from the neighbors. That's the spatial Bayesian approach. If you ever heard about MCMC or Bayesian, essentially here, I'm not going to details, you look at the book if you want, but basically the idea is that it actually takes it takes the value of the pixel, actually the logic of the probability of the pixel, and computes two distributions. The distribution of the actual distribution of the estimate distribution of the values in the pixel. Statistically, what you get one value, but in fact, probabilistic-wise, you actually have a distribution of possible values with the variance for each pixel. And the same for the neighborhoods. And that's spatial statistical theory. Not going to details, but you can basically consider the distribution of the pixel and distribution of the neighbors and take the average of that. That's called empirical-based estimation. And that's very traditional spatial statistics 101. Which means that if you go back here, you can do something called smoothing. So the smoothing basically is looking at pixels and looking at the neighbors and seeing what kind of information do the neighbors tell you. Why would we do such a thing? The details are less important than the concept. Why do you do smoothing? Why do you do smoothing in astrophysics?
So the problem I was confronted with is that from high-resolution images we can very accurately pinpoint the position on the sky, but the distance is still a problem because the distance uses a different kind of astrometry, so we get very large error bars in the distance. So assuming we have a spherical distribution of stars in globular clusters using the right ascension and declination extent of in coordinate-wise, creating a prior from that and then applying that to the distance. So basically narrowing down the actual distribution of the distances from what is being measured and from the two other extents that we can measure more accurately.
Yes, very good.
The only problem that I see confronted here is that one may have such a powerful prior that you're actually forcing yourself into a preset distribution from those priors that may not actually reflect the reality.
That is correct. But 9 times out of 10, what you get out of your typical random forest, Google Earth Engine, whatever classifier, is a map like this. Have you ever seen a map like this? What's the problem with this map?
That we have some distortion, some outliers, pixels.
Thank you very much. And that's life. Nobody's perfect, and life is even imperfect, right? Too short. And you have this lot of outliers. That's typical output from a Google Earth Engine story. But you don't want that, right? You want this. Right? You have this. I'm sorry. Let me get. You have this full of salt and pepper, as we used to say, and you want this. Right? But you don't want this in any way. You want this in a way that you can explain to someone that you have done a very nice spatial statistical technique. Even if it's not the right one, they would not know enough to... Nobody knows enough about these things. So you get away with it and say, well, I've done a Bayesian statistic. You know a Bayesian statistic? Oh, you don't know? I'm sorry, but that's spatial statistics. I'm sorry. It should be good. It should be good. Should be good. No, it should be good. That's life. I mean, come on. The only thing you learn, you know, after a long life is that some things are easier than others, and fooling people is one of them. Okay. No, but impressive. It's at least you got impressed, right? At the very first. And what I can tell you, this is sound mathematics. Of course, the whole issue here is that you are doing an empirical, you know, to be honest, what you're doing is an empirical estimate. And basically, this empirical estimate is smoothing based on some, that's not perfect, but normally the results are quite good.
So, if I get this correctly, you're looking at the different pixels and whatever class has been assigned with whatever probability to that, and then
Yes.
you're going to the neighboring pixels, and given the distribution of classes in those neighboring pixels, you reassign or just leave the original pixel in place.
Exactly. For example, go ahead.
How is this different from, very stupidly said, just putting a median filter onto that thing?
That's very good. Because the median filter, or you can do it, and you actually should do it, but the median filter, or something of this, first of all, a simple Gaussian median filter will blur your image. Just, we had it implemented, and it just blurs your image. Okay?
Depends on the kernel size, of course.
Yeah.
How much blur.
Yeah, the kernel. And the other thing is, you have a, I mean, let's look at here. You have typical effects here. If you look here, or this is a typical case. Can you see this? Mm-hmm. Okay, what's happening here is that life is not, the things we find in life, in real life, they're not discontinuous perfectly. So if you have, this was like a forest, okay? And this actually was an area of pasture. What happened is, there are pixels, Sentinel, which have a signal which is not only forest and not only pasture, but a mix of both. And that's very common in borders. And what the heck does the classifier found about it? The classifier, especially random forest, which is really a stupid classifier, it says, well, this is not forest. This is not pasture. This must be something else. For example, agriculture, whatever. And you say, but it's not. It's a mix of something. Okay? So then, oh, so then it's wrong. And then back to the median. And back to what it's actually doing here is something clever. Now imagine a window on top of this. And then you say, I want, picture, you have to imagine this is misclassified pixel, there's a window, okay? Everybody has like 7 by 7 window. I want to find the likely distribution of forest around the window surrounding a pixel. And the likely distribution of whatever, pasture. in the same area. How do you do that? That's a tough question, but I'm asking yourself. Go back to the problem. You know there is a pixel which is neither fish nor meat. Okay, and you don't want something else here. You don't want an octopus here. You don't want, like, you know, something. You're not vegan, so you don't want a vegan calculation. So you put a window on top of this misplaced pixel, and you want to compute some statistics. You want to compute, for example, the statistics of class forest, the statistics of class pasture, and the other classes. What should you do? If you, now, simplest thing, pick up the whole, you are on a border pixel. I'm sorry, I don't have it. You are in a border, okay? Remember, you are in a border, okay? Simplify. Half of the pixels in one side of the border are forest, half of the pixels are pasture. What's the best way to get the statistics of class forest?
Well, we could.
Counting the number of pixels in the.
No, you don't know that's class forest. You just know that this. You just know that the pixel on one side have more forest than the other, but you know that is a border pixel. Now imagine that you only take half of the pixels, you take the half of the pixels which has the highest probability of being forest, to compute the statistics of the distribution of class forest around that pixel. And you only take half of the other half of the pixels who have the highest probability of being pasture to compute the statistics of the pasture. You don't compute the statistics over the whole window. You compute half and half. Why? Because you want to get the best possible estimate of distribution for the class that sits on one side of the border, and the best possible estimate for the class that sits on the other side of the border. Then you have two distributions, and then you compare to the actual pixel. So is this more likely to be A or more likely to be B? And that's how you get this. You remove all the border outliers. Right? You had border outliers, and you have removed them. Let's get to the same area here. Okay. You had this border outlier here, and you no longer have the border outlier. You may have still a little bit, you may have to do a little bit more trick, but that's exactly the idea. And you get a much better result. Or at least the users like it better. Not necessarily better, but it corresponds, again, it corresponds to what a human interpreter would do by looking at the data. Clear? Even if the technique is not obvious. So if you want to learn more, there's a chapter in the book called Bayesian Smoothing for Post-Processing, which explains everything. And again, this is yours truly and another spatial statistician that got this. It's not available everywhere. I don't think it's available anywhere else. There's another way, which I don't know if I have the time, but I'll just point out to avoid this. I'll just point, if we have time, we go back to it. It's doing Obaya. How many of you have heard of Obaya segmentation? Very good. What to use for Obaya? Ecognition? Okay. Have you heard of spatial temporal segmentation? No, you haven't, but
I read it on your book.
you read it on my book. Thank you very much. Okay. So if you do spatial, I hope there's an exercise on spatial temporal segmentation on Kaggle. I'm just jumping around the clock just to see. Well, if you do spatial temporal segmentation, you also get much nicer results here. And by definition, as spatial temporal segmentations, the borders are nice. Okay? So that's another story. So did everybody understand the need for the smoothing? It's clear that we need to do something with the data, right? So smooth the data. Come on, do it. I hope it does.
One question while I start.
Yeah.
Is there a way to set seeds, like on seeds, So like that if you train the random forest once, that it will always train the same model? Because now I was just testing and running 1-2 times, and you always get a different variable importance or things like this.
Yeah. You now you set, you
Yeah,
put.
I tried that, but it didn't work. But maybe I just need to.
Now I have to take a look, because we should be able to, at least in Torch, we can do it.
Okay.
Okay. Why is it taking some time? Because it's lost? Have you tried, can you try to run on your own there?
It's running.
Yeah. It's because you only have 2 CPUs, so Kaggle is not a magic. On my machine it does. So, okay, just wait a little bit, so it's better than need some. So, and then after that, you finally get the point that you're talking about, okay? So this is the smoothed data, and after you smooth it, then you can do your classification. And, okay, go. It's classified and it's plotting. Okay, so now you get the plotted map here. And then we go back to introduction. So the plotted map should be like this. That's what you should get. Like this. Right? Nicely, By the way, the colors, the story about the colors, it's on the appendix of the book, but essentially what we have done here is to get, we've put up a list of all the colors that are used for either CCI or for IGBP, and there's colors for, a lot of these. But you can do your own colors. It's just that we provide a lot of predefined colors here. If you don't like it, you do your own. Okay? So, yeah.
Why 7 by 7? I know, 10 by 10, 20
No,
by 20?
oh wait, by the way, you can set it up. I just started 7 by 7. That's what that was the default. You can put 10 by 10, 20 by 20, 5 by 5. It's just that, let me explain why 7 by 7. 7 by 7 is 49 pixels, right? Half of 49 is 24. If you take out the center pixel, half of it is 24, right? 24. 24 means that if it's on the threshold of getting the right number of points for sampling a normal distribution. People say you need something between 20 and 30 points to sample a normal distribution. So we set the window at 7 by 7, whereas because if you're sampling half of the window, you get half of the points, and then you used to make a mean and average for the other half. So that's in effect you're using 24 points. But yeah, go ahead.
When we use large windows, if we have a strip of a glass, for example, a strip of a forest which is narrow and long,
then you might lose it.
Even remove it, right?
Yes, it could even remove it. And then again, why do you avoid there's the way, well, you do it, and there, to be honest, there's also a way of, again, it's a little bit outside of the course, but there's a way to change the hyperparameters for each class. Essentially, change the expected variance for each class. Classes which are quite narrow, like water, you don't think they are, you think they have a very narrow variance. In other words, they only valid, because if you take a spatial point here, there's water, water, and then land, 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 land. So you expect water to have a different variance than forest, 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 forest. And then you can control that. It's on the book, and if you have troubles, ask me. But essentially,
Because it's especially important for data such as emojis, because that's
yeah. But that's right. So that's why you can adjust this. But in general, I mean, I think that the bit here important is, again, not that you learn sits, but that you get the ideas. So the idea is, after you collected the time series, you could do, and you should do, some kind of estimate. Okay. So far, so good. So, which means we finished the introductory. No, that's fine. That's a lot. That's a lot of things we covered this today. Now, before I move the subject, do you have any points or questions or issues you'd like to raise? Anything that escaped your mind? Yes, please.
I just have a question. How applicable is it to SAR data?
I'm sorry?
How applicable is SIDS to SAR data?
Well,
What are the
that's a very good question, because I want to have the answer myself. In version 1.4.2, we just put now Sentinel-1. In principle, okay, careful. In principle, since we're dealing with values and we're dealing with time series, SAR is nicely organized in time series, you should be able to do a nice analysis with SAR using the time series in so much as the way that we're doing now. But there's a but. The problem with SAR data is that even when you come, for example, let's take Microsoft Planetary Computing. If you take, for example, Microsoft, there are two data sets, data catalog, Sentinel-1. You see, what you get out of Visa is GRD, okay? Which is good, but it's not the best. Microsoft has actually produced the RTC. The RTC is one of the best things you can get to work with, because it corrects for layover effects of SAR and so on. Now, it so happens that this is not open data. You have to pay to use it. But again, the problem here with SAR data is that even the GRD products that come out of Visa, into EWGRD, VH, and VV, they're good, but they still have effects, which theoretically have to be corrected with SAR. But I'll tell you more in 1 year's time when my course. No, I'm serious. We just released the support for Sentinel-1, but we have not gone through the full pipeline. And there is also, I mean, if you want to read, there's a nice paper by Charlotte and her student about, let's see, you probably know this one, it's a nice paper by this, okay, I like this paper a lot. How do you combine, I don't know if any of you know, who works with Stefan, the lady? Yeah, okay. So you should ask Stefan about this. He's a co-author with Stella. And basically, ways to combine optical and radar series using time series. And I think this is state of the art. Just for the record, it's not obvious how we can reproduce everything. Currently, in SITS, I think we can only reproduce this late fusion. I've talked to Charlotte about it, which is classify SAR first, classify Sentinel time series separately, and do some statistical operations of fusion. Okay? Okay? Now, back to the points. So just to finish up on this, let's clean a little bit this, because otherwise nothing works. Okay. Just that we go over what we got. What we actually did was, in fact, think about what we achieved. We did one command. Let's count now. One command to build the cube. Okay, one. And this is just explanatory. This is the data, so you don't have to do anything. This is description of the data and so on. But in terms of comments, we did another command to train the data. That's 2. We did another one to classify and get the probabilities. That's 3. We did another one to smooth. That's 4. And did another one to label. That's 5. That's 5 commands. And you can process the whole Amazon with 5 commands. This syntax does not change whatever the size of your data is. Okay? This is very important because, like I said, the lesson from Google is that you need a good API. So if you design your own Python API for doing what you want, remember, a good API makes all the difference. Try not to do what these guys did. Where is it? The one that we showed, try to hide this from your users, please. This code exists inside SITS, but it's hidden. You don't need to do it. Okay, now let's move. Shall we go for this other notebook called Creating Data Cubes in SITS? That's a very important bit, and I hope that you can start editing it. Because the whole business of data cubes is important. Like I said, it's crucial for any application that involves time series. Okay? So, do you all have creating data cubes in SITS, Kaggle? Good. So now, let's run. Everybody following? Good. So now let's install the bundle. Because each time, just to remember, each time you go Kaggle, it's a new machine, virtual machine that gets to you. So you have to tell the machine to install it again. So you install the bundle. It takes a little bit of time, but does it. It says session started, which is good. I like Kaggle. I mean, it's to teach us being, it's nice so you don't have to. Yes, it could, but you know, someone has to do it because you have to create a site, you have to test everything, run the bug. Of course, it would be possible, and I mean, it's just that there's 3 of us. You know, the whole development team is 3 people, so we have to be careful about what we wish for. Otherwise, I mean, we decided that we needed one of these, and we opted for Kaggle. Okay, so that it run, so you can run there, and you should be able to run SITS and SITS data. So please go up to this point where you run the library. So everybody should be at this point. Now, so now comes another necessary story. What is this data cube story all about? So back to the point from our Spanish colleague is, forgot your name. Lorena. Lorena. I shouldn't forget it. Okay. So this is ARD. So what they call analysis-ready data. In fact, analysis-ready data is a data set. It's an image, a single image, okay, that has passed, and the satellite has passed. And what you've done, you've taken each pixel on that image, and you first of all detected the clouds and produced a cloud mask for that image, that date, which is valid for all the bands. And you also took whatever values are valid, non-cloudy, and you made some normalization. The typical normalization would be correct for the sun angle and inclination of the seasons. You also may or may not, usually not, correct for topographic effects. And you may or may not, in some cases it's very important, that they're corrected by the sensor. If you're using Sentinel, that's not such a problem because the Sentinel sensors are very stable. However, if you're using Landsat 5, who has used Landsat 5 here? Just Loena? Oh, Landsat 5. So tell me about Landsat 5. Tell the guys about this marvel of engineering.
Well, it was a record-holding satellite, I guess, for its longevity.
Yes.
And basically, you had a unique chance to work with a sensor that has been built like long before I was born. So.
The 70s.
In the 70s, yeah. And I had to work. Basically, I was interested in water bodies. So you have a lot of noise in the image, and when you look at the water, basically, it's all you get is noise.
Yeah. Remember that it was not like Sentinel, which has a nice, like, charge couple device like this. No, you had a small sensor, and you had like a mirror that would come. Okay, imagine what does a mirror after you spend 20 years in space. So, I'm serious, if you look at the images. So USGS, you know why it lasted so long? There's a story behind it. Because there are two things that make a satellite live. One is the fuel on board. Because the fuel on board is the one that gives you the ability to go back to your place after you've been dislodged, because you get moving and then you go back. Now, when they built Landsat 5, they had the idea that Landsat 5 had enough fuel that it could go down and be fixed by the International Space Station. So it would go from 700 kilometers down to 100 kilometers and be fixed by the satellite, the International Space Station, and go back. Well, they did it to Hubble, right? Why couldn't they do this to Landsat? It would never worked. But remember they fixed Hubble. So it's not out of the question. So that's why they had so much fuel to last so many years. And the mirror, of course, going back and forth, the quality of the image vary over the years, and some data is very noisy. But nevertheless, the data is there. And USGS is doing the best to make it comparable. Again, you may have places where there's data, there may be places where there's missing, you may have anything. Sentinel, in that respect, is much better. Sentinel, it's nice. Sentinel 2. No, Sentinel 1 is another story. Whereas Landsat is like this, okay? Now, what can you do? So what is out there? What's out there, as X-Files would ask you? So Amazon Web Services has, in terms of open data, it has essentially, well, the data we support now, there's more data there, but essentially currently, but I'm going to give you examples of Sentinel-2 and 2A. The Brazil data cube is for Brazil, which is already a Sentinel, CBUS, Landsat, MODIS, but organized as regular data cubes. I'm going to go back to the regular data cubes a little bit. Digital Earth Africa was a very nice. How many of you heard Digital Earth Africa? Yeah, it's very good. They have actually data on Cape Town, and then they have open data collection of Sentinel-2 and Landsat 8. And then there's Microsoft Planetary Computing, lots of data, including Sentinel-2, Sentinel-1, Landsat 5. USGS, I don't know why the Americans are so crazy that they made Landsat available, but you have to pay for it. And there's also a nice thing for those of you who like LITESO data is the harmonized Landsat Sentinel data, which is NASA did, and NASA did the following. It's Sentinel tiles, well, it's Landsat combined with Sentinel at 30 meters on Sentinel tiles. That you get Landsat and Sentinel harmonized. Now, let's look at these data sets before we close for lunch. So let's go here. I hope you have, no, let's, come on, I'm looking at the wrong, okay, we're back here. Okay, so what's the difference between an image collection and a data cube? Like I said, an image collection is the images as they come, they're corrected, but they're not necessarily in the right projection, they may have gaps, where in principle a data cube has no gaps. And the data cube covers a region of longitude, latitude, and time, may be split by tiles, so that you can select time and you can select space. If you take one instance, you get the bands. If you take 1 point, you get the time series. So let's access this. Let's see if we can run this here. This command, can you try? Have you tried? Okay. So can someone explain what I'm doing in this command? Should be fairly obvious, I think. And again, if you write, what am I doing while it is running?
You're getting the data from Amazon, you specify the collection, what types you need. You select just 4 bands.
Yes. You could select any bands, I'll just give you an example. And you select the start date and the end date. You know, very similar to Google, right? In Google, you said image collection, da, 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 da. Yeah, of course. We looked at it and liked it. And then you can plot. Now, this here, this is not a regular cube. This is the collection that it comes. So, I think in the plot, we selected the date, which I think has the data covering the full tile, but that's not necessarily the case for every date. And I think in this date, there's still clouds. So it's not necessarily cloud removed or tested and so on. But that's the first step. By the way, I don't know how many of you know about Stack. You know? Have you used it? Okay, Stack is the protocol that is now being used as the protocol for Stack browser. No, this is a Stack browser. About Stack, stackspec.org. Okay, so this is essentially a specification of a spatial temporal catalog. And essentially is a language for describe geospatial information. And if you want to go like bare metal, heavy metal, and you want to access AWS, you can actually use the Python Stack API or the R Stack API or the Junior Stack API to go there and select your things. Now, in this case here, what's happening? Oops, it didn't like me. Why didn't it plot? Did it plot yours? Well, it should be plotting. So behind the scenes here, what's happening is that it's using Stack to query the Amazon service and asking Amazon, what are the images here, what da, 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 and then gets back those addresses, and physically address. So this S2 MMU cube, it actually has a physical address of a band in Amazon. It says, this is where, okay, so, oh, nice. Obviously, this is Brazil. Nice place on the coast in Brazil, nice place for vacation, warm and nice, but of course with clouds, because this is just ARD. Close, what's sort of close to where I was born. So just to make sure, if you say, for example, S2, what is 23 MMU cube $file info 1 $path 1. What is the so if you type this, okay, you should get something like this. So what is this strange address here? Can anyone tell me what is this?
Where the band blue of Sentinel-2 at that day stored.
Yes, this is actually the actual physical address of what this data is in the S3 bundle in Amazon. And again, if you actually use GDAL, who knows about GDAL? Everybody here? You can actually do a GDAL info on this. So if you can, I'm not sure we have GDAL here, but you can actually use GDAL at this level. You don't have to. We actually use GDAL, but you know, to do this plotting here, we obviously use GDAL to open the data and show it to us.
So basically, there's no need to download the data.
No, there is a need to download the data. It's not necessarily download the data, but there is a need to regularize the data. That's the point. I'm going to briefly give you 2 bits of information, and we get back after lunch. But to answer your question, okay, here in the book, I'm showing how to access Microsoft Planetary Computing. You would see that's about the same thing. So you say, oh, I now at Microsoft, this collection, and so on. And this, you have this image, or the Landsat collection on Microsoft, or the Sentinel collection on Sentinel Earth Africa, or the CBUS collection on Brazil DataCube, whatever, the harmonized Landsat collection on NASA. But the problem is the following. Okay, let's take this. And I'll take 2 minutes out of your lunchtime, but we get back to. Okay. Now let's consider a real case where I am running, I want 2 tiles from Sentinel. I want 2 tiles from Sentinel, and I want these bands there, in these dates. My area covers these 2 tiles. So I go to Sentinel, and I ask, I go to Microsoft, and I say, okay, 4 tile, 20 LKP. Between these 2 dates, how many images do you have? I have 7, 8, 9, 10, 11, 12. I have 12 images between the 1st of June versus July and the 31st of August. Now, and what about tile 20 LLP? I have 24, right? You've counted. Thank you very much. So it's not the case that 2 neighboring tiles will have the same number of images. And how on earth are you going to do an analysis or time series with one with 12 times and other with like 24 times?
You need to fill the gap.
You either need to fill the gap, or you need, again, remember, the fact that you have images on that date does not mean that the images on that date cover the whole tile. So for example, 20 LLP on date 3rd of June of 2018 is this.
And it also depends on the instrument. For example, for Sentinel-2, the same tile, when it's we are using A, it's not the same as we are using the instrument B.
Right? Therefore, which means that you cannot do a full analysis with this. So in order to be able to go back and have a real data cube, that's the whole trick here. What you're here, you need to come here. You need to what we call regularize. Project a regular data cube. And that I'll show after lunch. But essentially, we're going to show, and again, the principle is what it matters. We're going to show that, yes, what I need is to produce a data set that for the areas which I want, which are 2 tiles, has the best estimates for the dates which I want and has no gaps. In this case, it's very clear, and I'm sorry, it's not my fault, it's Caesar's fault, that the images have a difference. They shouldn't. If their analysis is ready, you should not have to see this. Okay? Fair enough, but that's another story. The fact here is you will need to produce regular data cubes in order to proceed with time series. So that's, I would argue, the condition that we need to go for. And in this case, back to your download, you actually, if download means download to your machine, yes, might be download to your machine or download to any place you are. You might be, as I normally am, on Amazon, directly with a virtual machine, or in Microsoft with a virtual machine. Or if I have, for example, Amazon gives me, I'm sure Microsoft gives me, Digital Earth Africa gives me Jupyter Notebook with R. So you use the Jupyter Notebook with R in Microsoft and you run that. But the principle here is, back, that you need to convert your collection into data cube. And then you're in business, okay? For now, I think we can break for lunch, and I think we're back at 2 o'clock. Is it the time? Yeah. Okay, so have a good lunch, everybody. If anyone wants questions, I'm available.
I have a different question.
Yes, go ahead.
Yesterday I tried to install the libraries on my PC locally. But when I went to install SF, so install.package SF.
What is your machine?
Arch Linux.
Arch Linux, okay.
Yes. And
And
they
what
get
happened?
compilation errors. It doesn't compile.
Because now it's a good question. CRAN sits, let's see. I mean, CRAN has tested these. CRAN has said that it works on Patch Linux. Is that what you have? Debian, release Linux. Here it says okay, but let's see SF. Oh, go ahead, Emilia, did you get it?
Yeah, I got it.
Okay, so where's SF? SF here. Let's see, CRAN check. It says okay, but let's see what the answer says. SF. Let's get to GitHub.io SF. Installing. Install Windows, Mac OS, Linux. Ubuntu. You have Arch. Which one you have?
Arch.
Arch. Did you do this?
No, I didn't.
Go to our spatial Git. Okay, let me show you how I got there. This is called SF type simple features for R. Okay, simple features for R SF. So R spatial GitHub.io SF. Simple features. Does everybody know what simple features are?
No.
No, you don't. The others? No? But yet you use Python and pandas. Okay.
I know I'm not perfect.
No, okay. Let me explain. The story behind simple features is an interesting one, why people get in, and we can tell it. So the whole issue here is that in the 80s, people were trying to do the basic, get computers to do maps. And they were struggling with some basic things of interoperability. And then some researchers, and I want to, some researchers said, okay, there's complicated things and there's simple things. And they said, what is the simplest thing in the planet that I can do? Okay? The simplest thing in the planet that I can do is to define a closed set. I'm sorry, went back here. Do they have the, I wanted to get the, no, why is crazy? Okay, so what they did is say, okay, there's something called point, which is a point. That's called a line string or a multi-line. A line string is a line that is continuous. And then there's something called polygon, which is closed. So it cannot be a polygon if it's self-crossing. But of course, a polygon can have holes, and there's a multi-polygon and so on. Now, a lot of things can be represented in the computer by a simple feature. A lot of things can't. And so what they did is say, let's take the easy one first. Let's define what are these simple features. And then let's define a set of operations. Simple features 9 intersection. A set of operations which define, okay, this is, so when you say meet, overlap, equal, this researcher called Max Igenhofer, he's German, but he is in Maine for a long time. And Max said, okay, let's define these relations formally of simple features. And then it was extended. And because it was a closed definition, it was equivalent to the relational model. You know, relational model. It's, you know, relation, operations on relations, and out of that came a multi-billion company, Oracle and the other database. And here, what it says, this is two-dimensional geometries with a certain properties, and given these two-dimensional geometries and a certain properties, I can define operations on those, and that everybody should follow. So this became a standard adopted by MySQL, Monet, PostGIS, Spatialite, Oracle, whatever, R, GDAL. I suppose there is a Python one. I know SF does it, GDAL does it, Degree, I think there is GeoPandas does it, and so on. So they all adhere to a standard, and we call them simple features. So it's not an R thing, it's a simple features standard for R. That's SF. And then back to your friend here, my astrophysicist, who says you need to, and behind the scenes, it needs GDAL, it needs Proj, it needs Geo, which is the basic libraries for spatial data, which everybody uses in the end. So simple features are, they take care of most needs every day, and people have adapted to using them. And a lot of what I do when I need vectors uses simple features, and everybody else. Okay? Good. So we're back. So please, we probably need to restart the machine, so the creating data cubes, and just that we get back here. Running. Okay. Plot and library. I hope Emilia has gotten back to where. Thank you, Emilia. Very good. Okay, like I said, there are places where you can get your data from. We showed how to get data from Amazon. Again, we showed that the Amazon data, the path for when you get the data is actually a file who is somewhere on Earth, in this case on US West, somewhere in California, in an Amazon service. Sentinel, And of course, you can do the same for example, Microsoft Planetary Computing. So if we click here, we get the same story, no news that it works. Again, it's a basic mechanism that you ask Microsoft, what do you have? In Sentinel, do you have this data, this style, this man, and give me the images of bands 05, 8, B11, and cloud that correspond to this region on Earth and this date. You get it. And this, you can do it this way. You can ask, do in Python using stack, many ways to cut the cake.
Where do you put the credentials for the backup?
Aha! Back, you don't need, so, we put it for you.
No.
Yes. Yeah. And why is not plotting? Now I don't like it. We get the credentials from Microsoft and we put it to you. Why is this not running? And then we keep it for some time. In fact, I've been supported by Microsoft, so yes, we're giving some.
Brazilian data, no?
Huh?
Only to use the Brazilian data or at any location?
Of course. Try it. Give me a tile. Try it. I mean, SITS is not meant to be used for Brazil. Give any tile. Just type, give me a tile in Croatia. Give me a tile. Come on. 35 ULA. Sure? Okay. What about?
Okay, so this is Landsat now.
No, this is Sentinel.
Sentinel-2 from the Microsoft.
Yeah, but it could be Sentinel-2 from Amazon. And I hope that someday, sooner than later, will be Sentinel-2 from... okay, wait. Let me take... No, wait. I have to do it 2 steps. Because I'm asking for a date, but the dates that I'm going to plot are not... Okay? So now, it's getting for 35 ULA. Okay, good. It's got it. Let's ask for the timeline here. Sits timeline. Oh, I still put S2 LKP, but you will not be mad at me, but it's 35 ULA. Okay, so these are the dates, okay? So let's type 14/7, so plot. S2 20, it's 35 ULA, you see in a minute. It's just that I misplaced the name, MPC. So we're going to put red equals band 05, whoops. And then we're going to put green band 8A. And then we're going to put red equals band 11, just for argument's sake. And date equals what have you, 29. Okay, let's see. What's happening here? Let me try again. 20, S2 35 ULA. Cool, my. Oh, it has to be. Nothing that, otherwise, don't disappoint. Okay, let me see. Okay, so what's the timeline? 35 ULA cube. Yeah, 14/7. Okay, S2 35 ULA cube MPC. What do I get? Yeah, Sentinel-2, MPC, PGG, EPSG, bagara. Yeah, lots of it. And then if I type, which bands did I ask? 05, 8A, 11, 35 ULA, cube MPC. Okay. Whoops, 35 ULA, cube, MPC, red, green, blue. Okay. Argument red.
You put 2 times red in the arguments.
Oh, sorry. Thank you. Saved by the students, by the audience here. Okay. So we know, we'll find out what 35 ULA means. Only Emilia knows. Somewhere in Romania, right?
No.
Where is it? Well, it says 53 north, 24 east. Huh? Lithuania. Yeah, you can try another date. Let's see what the other date says. What? 4/7 of 2019. 04. Let's see if we get a better image. Oh, these. So again, that's the answer to your question. There is no. I mean, You can use it for anywhere.
Okay.
Okay? There's no.
Is it archive data or is it updated
Yeah, so
with the new?
can we use it with the data of the last month, for example? Yeah.
If the data is on Microsoft, yes.
Okay.
It's still that in the season, that's a lot of clouds, so you probably need a less cloudy season.
And how about the processing? Do we pay for the Microsoft?
Okay.
Or because
Now-
it's another
No, no,
issue
no, no.
if you want
Okay.
to run
Up to
more-
now, you didn't pay anything. I didn't pay
Yeah, up to
anything.
now we didn't, yeah.
Okay. Now, just to answer one last point. Now, of course, I think the question was, can I select based on a region of interest? Yes, I can select based on a region of interest. It's how. I'm going to skip the Brazil data cube. Now, we're going to skip a little bit things. So now that is the point where you start making your options. Okay? So here is where I have, first I'm creating a data from AWS on an area in Brazil with band 05, band 8A, band 12. And I'm not going to pay for it. Now, when I start paying for it, I may pay to someone, to myself, or to Microsoft. And now that depends where the next step after you've done your data cube is. And the next step is, where are you going to put your regular data? Up to now, the only information the system has is, well, there is data out there. There's data about my area. And you actually could ask, for example, Emilia, if you type summary, if you type data for a whole year, if you type summary, one of the things you get, for example, is the cloud cover for each image, if you want. Where someone in Poland was asking me this question the other day. Okay, now I have to decide. Up to now, I don't have to decide anything. I just say, I just found out what's there. Now, the next step is, okay, what am I going to do with the data? And that's where you have to decide, and this is this nice, of course, that would in a different system, you would do very similar choice. If you want to build a regular data cube, where are you going to store your data? And then the options, there are many options. One option is, of course, to store it your own computer. The other option is, if you are running on Microsoft Planetary Computer offers you some notebooks. Okay, so that's the one we have here. That's one image from Microsoft, or from Amazon. But for example, if you go to the Planetary Computer Hub, for example, already have an account. I hope I have an account. Sign with Microsoft. Microsoft all the time tries to. Oh, come on! I never know my password. Okay. No. No, only there's no one from Hungary here, so.
Yeah, I am.
You're from Hungary. You're from Hungary. Okay. What is the code from Bela Bartok, en plein air sonata? You know Bela Bartok.
Yeah,
You know the sonata in plein air.
Yeah, and the register code of that. I don't know it by heart.
Okay, thank you very much. But it's only part of it.
Don't worry, still probably
No, but it's been Bartosz. Why is this complete?
Are you playing it by the
No, I love it. I love Bela Bartok. I'm a great fan of Bela Bartok.
Thanks, guys.
And then also, let's see, and Kodai also I like very much. And Ligeti. And Ligeti. You love Ligeti?
Ligeti. Yeah.
Kurtak?
I mean, this is, we have the Ligeti music school system.
Ligeti is great.
The guy who goes to the piano.
Oh, come on. I'm getting Microsoft Authentic. Microsoft is making fun of me in front of you. Where's the Microsoft? Authenticator. So I have to come up here, Authenticator, and then 66. Face ID, fine, stay signed in. Yes, please, stay signed in, come on. Let's get your Microsoft account, sign in. Forget it. You have to believe me.
Microsoft style user experience.
Let's see. I have another account in Microsoft. Okay. Azure. Sign in. Oh, come on. Microsoft Online. Ah, God. No, that's not it. That's not it. Yes, thank you very much. Not now. Send notification again. 94. It's a fantastic, as you can see, it's a wonderful experience. Try Face ID again. Oh, come on. It's okay. Okay, you can hope. Believe me. Believe me. I hope that you can enter the. If you go to the Planetary Computing Hub, log in, create an account. There's a free account for Python, there's a free account for R. In my case, I have support from Microsoft, and I have different virtual machines. Then I really run it on, for example, this is a machine with a GPU. And there I have different machines here. In this case, you're running on Microsoft. So I'm getting the data from Microsoft and running on a virtual machine on the planetary computer, which gives me speed at a score of money. But there's nothing that prevents you, in principle, if you work in a small area, to be able to select your data. In this case, for example, what I have, first of all, I selected the data I need for a certain period in a certain tile. Now comes the trick. That's the important trick. You will regularize the cube. Okay? And regularize the cube is simple. You say, this is my origin of the cube. This is the output that I want, and the output is somewhere where you want to put your data, local computer, virtual machine, what have you. The resolution is the output resolution. In this case, I'm putting 120 meters just to speed up. And then the period, which is very important. 16 days, in this case, I'm betting 16-day intervals. You can have a month interval, whatever you want. Again, just not to get ourselves into too much DR world. My point is whether if you want to do it for time series, you need to do something like this. Not exact, of course, not this exact command in Python or Java or whatever, but you need to do something similar. And I am not sure. I'm sure in R, there are packages. I mean, instead, just to be honest, if you use R, we use a package called GDAL cubes. And I think there is a version of GDAL cubes for Python. Well, it's a C++ library. I don't know, it should be able. It was originally developed by Marius Appel in Munster. I've never used it on Python, but it's a C++ library, so in principle you need to check with him. But back to my point here is that you need to do something like this, otherwise you're not in place. And this is where, again, someone is talking about, that's not, you sort of can get it from Google Earth Engine, but not exactly.
It takes the first valid pixel value out of the 16 days period?
It takes, okay, the first question it asks starts from the first 16-day period. Now, in 16 days, how many Sentinel images you might have? You don't know. Maybe 3, maybe 4, maybe 5, maybe 6, depending on the place, on the satellite. So it looks at the 6 images and looks at, first of all, ESA gives you the information about clouds.
Yeah, the STL mask.
Yes, that's right.
So let's say 4 out of the 6 is...
No. Remember that there is a different, in theory, there's a different cloud for each data.
Yes.
So what do? You start with the image with less clouds. Okay? Bang. So you already have a lot of pixels, and then you have pixels with clouds. Then you look at these pixels with clouds. Then you look at the second next images without clouds, and look how many pixels which have clouds here, have no clouds here. And you get those.
Yeah.
And then you go to the third image, that fourth, fifth. And then if you ever, the 5 images, for example, you still have clouds in all of them, you keep a value that say, I don't know anything about this, it's called an NA, and that sits there. Because remember, you're building a cube for a large area. So imagine that you have like 15 days. For a year, you have 24 images.
Yeah, but then, so the question that it takes the first in time, which has no cloud information.
Yeah, within that period.
So it's in a time order.
Yeah, remember, within the, again, the question here, when you do, let's conceptually, when you regularize things on a period, you're going to assume that within that period, there is not a big variation between the values in the images.
Exactly.
So within that period, you take first whatever image out of the 5 has the least clouds. 1, 2, 3. No, you start with the, there are 5 images there. You ordered the image by less clouds. Okay, this one.
Yeah.
And then clouds here, look at the second clouds, look, and then there might be after this still clouds.
Yeah, and the question was that if you have like in the 16-day period you have 3 pixels without clouds, then it would take the first in time and not like randomly or an average.
No, it doesn't take the first in time.
No?
It takes, there are 5 images.
Yeah, but let's pretend that we have still 5 with 0 cloud.
Oh, then it takes the first.
Then it takes the first. Because there is another model to use where it took an average, for example. If it finds 3 without cloud, then took the average of that one.
Well,
But okay, it takes the first.
I don't like averages.
No, neither do you. Or you can do like randomly takes one of it. But
Right.
yeah.
But the other important bit is that if you're taking now a year out of data, okay? Remember that whatever you do, you regularize and you have a year's worth of data. A year's worth of data, you have 24 images. maybe in a year, out of Sentinel, you may have 100 images. So you boil down to 24. Some of these 24, remember the ones Amelia was looking at Latvia? It may still have clouds. So, yes, but then you need another step when you're classifying, which is interpolating. If there are missing pixels, you need to interpolate in time. So imagine that I have an image here with a pixel, a missing cloud, another one. I have to interpolate this one to get a nice time series. I cannot just leave it there. Otherwise, my time series is lost. I need the information for every pixel. So you need to be able to recover, by interpolation, between two valid pixels, an invalid pixel, and estimate the value there. Of course, because after, huh? Yeah, you know the, yeah, you can, but you do it dynamically. After you regularize, you have like 24 images. So let's look at the clear example. So now we finished the data cubes. So let's go back here and take working with times. Please take a look at working with time series. Okay, let's see. And I'm going to see. No. Oh, okay. Yes. Okay. Fair enough. So please open the notebook Working with Time Series. And we're going to be brief here because we have about an hour left. So I'm going to go a little bit. So back, Working with Time Series. Again, we install the package. Okay. We install the package. So back, everybody should have this, okay? Is it okay, Lorena, you got it? Okay, Amelia got it? Okay, so it should be installing the bundle. The nice thing is, of course, that you can, on your own, take a look and run all the exercises back home. They should work. And then load sits, and just to get the graph output. And I've already shown it how to do the time series, visualization, and so on. I want to go to the real thing. Okay. Okay. So remember the simple procedure that we are doing. The procedure that we are doing is nicely summarized in this slide. So if you understand the slides, you not only understand the package sets, but what you have to do in order to be able to use time series. So keep that in mind. Because it's very simple. Things are simple. There are only two things in life. The very simple, the three things actually. The very simple things, the complicated things, and quantum mechanics. And provided that you're willing to believe my Niels Bohr. Okay, but the learning consists on transforming complicated things into simple things. Simple things are the ones you know, complicated you know what. And quantum mechanics is the more you try to learn, the less you know about quantum mechanics.
It's not that hard.
Huh?
Exactly, it's not that hard. You just have to assume that it works. Yes. It's like
It's right. Very good definition. But I still maintain the three things in life: complicated, simple, and quantum mechanics. The rest is trivial. But this is the simple. I mean, I tell you, time series is simple. Learn that. That's all you need to know. You need to know how to build a cube. That's what we discussed. You need to know what samples are. You need to know how to train the model. We show how to train the model. And then you need to know, there's one bit that we didn't show. This is this graph here, how to get the data from the cube. Okay, that's what we're going to show now. But everything is really simple. I mean, quantum mechanics is hard. I've tried so much to learn it. And there's a book by Philip Paul called Beyond Word. Have you seen this book? Oh, it's wonderful. You don't feel alone in the world any longer. Okay. So so you should be here in the same saying obtaining time series data from data cubes should be at this point, which is exactly that arrow that we're showing earlier, right? So that was the arrow we were showing. Okay, this arrow here. That's what we're going to do now. Get data. Okay, everybody fix here. Put your mind to this and things will work. Get data. Good. So let's get data. The first thing we need to have is a data cube. And here I've created a data cube. Basically out the same data cube we started in the beginning, out of local files. So it's the same, the one we explained. And then I'm asking a simple question. Give me a time series in a place. I have a place, latitude, longitude, which I went there. I know where the label is. I just want to get the time series. Okay? And then, okay, I have lat long. I say, get me the data. This is my sample, latitude and longitude. This is my cube. Give me the data, please. And then it says, okay, as a series, plot this time series, please. And you get it. Okay? It's there. Oh, but I need to do, well, latitude and longitude is, not real. Let's do something better. Let's take a CSV. Okay? So someone went to the field, got me a CSV file. What does this CSV file look like? Come on. What is this CSV file? It's a CSV file that I read with 4 columns. Typical thing that you get from a field work. Someone said, I went here, and I can tell you that from this date to this date, this was pasture. Okay? And you might have hundreds of files, hundreds of points, thousands of points, what have you. And what do? You want to get the data there? Very good. Get data. Same, okay? Here you just pass 1, here you pass a lot. The end result is the same. You get your values. That's what you want, right? You know that in that place there is something, but you don't know the NDVIs and EVIs. But then, okay, get me this NDVIs and EVIs, put me back. Okay? This is here. And I can, for example, this is points, dollar time series points, first line of points, time series, Or what? And boom. Give me the time series of the first point. Okay, the time series of the first point is this one. Plot me, whatever. And then it gets you 1,000, 50,000, whatever. And I remember once I had my bladder removed, and I was sitting in the hospital, and they say, okay, you have to sit there and don't do anything for 3 days because we need to know if there's any reaction to the operation. I said, what am I going to do in the 3 days? Oh, I'm going to collect some sample points. And I collected 20,000 points in 3 days. Well, I mean, nice thing to do. Okay. Wait, but, okay, but what if I have shapefiles? Yeah, shapefiles, okay. For example, this is a shapefile in a certain region, okay. This is a big state, and I want to collect some shapefiles here. Or I could have a set of shapefile coming from a data source like Euro crops. There's lots of crops when you have shapefile with polygons and labels. Okay. So here it reads a shapefile. It actually shows you that. So here's a shapefile from a place in Brazil. And then, for example, you can say, you can create a data cube, okay, out of that polygon or that, area. In the case that it's a very large state. But in here, I'm actually going to the Brazil data cube, the MODIS collection, 2 bands, passing on the shapefile, which I'm masking, and saying, okay, I want the cube from big cube, 1st of June of 2020 to the 29th of August of 2021, more than 1 year. Okay? In this case, the Brazil data cube is nice because all the data there is already regularized. No prizes for guessing that, of course, the guys in the Brazil data cube know that it basically SITS is the software that's used for the Brazil data cube guys, but it's not referred to Brazil. But as a courtesy to the users, the data on Brazil data cube is already regular.
There's no fun.
And then what I'm asking here, after I get the cube, I hope it works, is give me 20 points inside this polygon. And I could actually put a label here. For example, you want 20 points out of this polygon because you know someone, and of course this is one polygon, but you could have thousands of polygons. For lots of databases are available in Europe with shapefiles, with labels. So it's going there, getting the points, giving it back to you. So this is all you need to get the data. You can say, okay, standard shape, you need a cube and either CSVs, shapefiles, tables, what have you. Simple. So essentially, this is what you expected, right? This is how it should work. You tell the system that you have, this is how your samples are organized, how your data is, get me the data. Simple as that. Nothing. Yeah, that's what it is. So I hope it is running a little bit. So what I'm going, we have 45 minutes left, but it's time if you have any questions before we switch to any questions on the get data? It should be simple, and it is. Why complicate?
Get data is like pixel-based, right?
Yeah, get a time series, because time series, pixel in the sense that time series, you pass on and you get a time series. That's what you want.
And does it also takes into account the date of sampling?
Datum sampling, what do you mean?
Because you have samples taken on a specific date.
No, yeah, what I'm saying, the data,
And there is also, start date and date in the samples file.
there's also start date and date. So you can, essentially what you mean is that you can basically, when you have a start date and date of the cube, and you have a start date and date in your samples, the only restriction here is the start date and date in your samples has to be smaller or equal inside the period of the data cube. Right? If you have a 20-year data cube, fine. And then I only want for 2 years, 3 years, 1 year, half a year, whatever.
You actually need to select minimum and maximum data when you retrieve
Well,
data.
oops. Applies.
Rich display.
Rich display and wrong. I'm gonna.
Trace back.
I am. No, I think I know what is happening here. Let's see. Let's see. Could it be? No. There's a problem retrieving the data. I'm going to have to pass this one in the interest of time because this is something strange here. I have to check, and it takes time, which I don't want to use right now. Because essentially, this is an example which I tested yesterday, and it worked. But I'm apologizing, but this should work nicely. But, sorry. But bear with me. If you have a problem, you can always, if you ever decide to use something sits and you find a problem, you can always ask for help. And as any good open source software, you probably know, those who work with open source software know the protocol. The protocol is you get to the website of the GitHub, and then you open an issue. So you open an issue, and we hope that someone comes to rescue you.
But you read the previous issues first.
Happily ever after. Okay, but I think I'm going to skip this a little bit because what I'm going to do in the interest of time is go over two things which I think it's important, and I'm going to go into the machine learning for data cubes. Please go to the machine learning for data cubes. Because this is, after all, some of the issues which will be involved. And here, I'm going to just skim the whole idea because there is nothing we're going to again, if you go back to the machine learning for data cubes, and again you have to start the Kaggle setup. And what I'm going to just give you is what is the logic behind the machine learning, because I'm going to use this in the examples I'm going to show later, so that you have a sense of what is going on. I know, so again, the same thing, you run the bundle, and then you run the installation, and then we start by looking what's available. Okay. So what's currently available? You have random forest, support vector machine, extreme gradient boosting. These are the traditional machine learning methods. We had implemented light GBM. Don't know if anyone knows light GBM. In fact, we took it out, but now it becomes, if you want to, sometimes, I don't know, some student might want to say, oh, I'd like to test my own code in SITS. Okay? I don't want to use SITS. I just want to show how good I am in developing a classifier. Okay? So there is a session here including new methods for machine learning. And actually the example we give is using light GBM. So in fact, light GBM exists, but as a, and if you ever want to go the full deep learning mode, you can essentially go and take a look at the how the deep learning methods are organized. So I know Andrea is working on a thing called LTAE. So Andrea, if you ever want to look at this beast here, you're welcome. I don't, you know, he already have done it once, so you may well do it twice. No, it's a code which is so strange that it's only when the Germans did it. You know, it's a French guy, very nice French guy, but, you know, he's not the best programmer around. So there were German guys who actually did the BMW Vorsprung durch Technik thing, and they rewrote the code. That's the address in there, from Maja Schneider and Marco Körner. And so it's very Vorsprung durch Technik. It's the code is much better to understand. But again, this is everything that goes. You never see this. You shouldn't. But basically, this is a and the same. The arguments are the samples and the method. So that's all you have. There is to it. And here, what I'm doing is taking a point in 17 years, and I'm classifying the point, and I'm plotting it. This is the plot. Looks good. Like I said, random forest. There's a problem here, but it's not a trivial problem, and I'll show you later. But essentially, random forest gives you that. So it says this was an area of forest which got turned into pasture and then went into soy corn agriculture. Thank you very much. And again, this is those that I think, don't know how many of you know about convolutional neural networks. Okay, so this is TEMP-CNN, convolutional neural networks for time series. Okay, so here I've put, so you can run it now. And of course, I put more information than I normally would just to show you what's happening. You could just say temp CNN, opens, close. Or you could say lots of other things, like optimizer, CNN layers, CNN kernels, dropout rates, epochs. Normally, you should not worry too much about it, unless you're into really getting the last bit out of the model. But again, in principle, so it takes some time because it's now running, so you need a little bit of patience. I hope you have a little bit. It's another, I would argue, this is like my baseline deep learning model. It's like random forest for a time series deep learning. Because it also gives you a nice result, not necessarily the best you can ever get, but again, it's also sorts of reliable. And you can see here, this is, you can see, I hope you can, everybody understands this plot? Anyone does not? Well, this is, I'm asking, I was very conservative. I've asked it to run only 40 times. Normally I would put more. And I'm asking it to run 64 batches in each time with 3 layers of 128 elements and a kernel of 7 for each and a dropout rate. And then there's a whole explanation of dropout rates. And within within the 40, you can have the train and the validation. So the training is what it gets out of its own data that's using the training, and the validation is what it's getting out of the test data. And this is 95%, okay? And then you see the accuracy. So if you do a little bit more, it actually stabilizes. At a certain point, stabilizes. So now that you have the temp CNN model, you can do the same thing we did for the random forest, which is classify the point and plot it. So, bang, and here. And it's interesting. So let's compare these two. So that's random forest. That's temp CNN. And here it says soy cotton. Okay. And here it says pasture. So clearly between forest and pasture, it's very unlikely that someone has put soy cotton. Does that mean the temp CNN model gives a worse result than the random forest? Yes or no? That's a tricky question, but I think it's one worthwhile asking. You see the result of random forest, okay? And then you see the result of temp CNN. And I'm just comparing this year here, where it says,
yeah, but when they cut out the forest and you know the rest of the mulch or how we call it remain there, it could look for a few months like an arable land.
yes.
Because it takes a while the
So what's the
herbaceous forage is overgrowing the crap left there, you know what I mean?
So what's happening here?
It's a more sensitive model, just it classified that to the arable land nature.
And which indicates that,
It's the better one. Just
and
to
not only it's the
understand.
better one, but it's also a message to the modeler
Yeah, that you have to train it for that one.
that you're missing a
Then
class.
you miss that kind of training information.
You
yeah.
miss a class which is neither fish
I don't know
nor
how to call
meat,
it, but
which is the deforestation.
Yeah.
It's not there on your data set. Since it's not there on the data set, it has to put it to someone.
Yeah, I mean, that human brain retrain.
Of course, it's not the human brain. So you would always blame someone. It's like, you know, that judge that has to find a culprit. So there's always a culprit, but not necessarily the right one. So you're absolutely spot on that the temp CNN is more sensitive than the random forest. Again, random forest gives you result. And in principle, you should be happy. But the other, and then again, those of you, I don't know, how many of you have learned of attention-based models? Andrea has?
Yeah, I learned, but couldn't run yet.
Okay, so there's this.
Theory, but we want-
No, I mean, there is one researcher called Vincent Garnaud, which has developed these two models, the PSE TAE and the light TAE model. Again, the whole idea is, don't think I have the time to explain, but it is a very simple transformer model. But still considered by some the current state of the art in image time series, satellite image time series analysis. And unless Andrea is going to produce a better model in his PhD thesis, and we shall wait for him.
Actually, in the repository for the LTI, there are now a better result achieved from another network, which is another type of transformer network.
Oh, is there?
Yeah.
In the same? Okay. So I'll look into it because. Okay. So. Again, you can have this. I'm not going to run this because it takes some time. But here what we did was we trained the model and we classified a single point. Okay? And we compared two models, deep learning, not deep learning. Before we go into the same story but classifying a data cube, let me just state for the record that there is something called model tuning. Okay, so SITS offers, and you should, if you work with some other packages, also consider tuning your model. But then, please use a GPU. Or, please run it before you go to bed and hope it gets ready when you wake up in the morning. Okay. In this case, I'm not going to run here. I'm going to say it makes a difference, a small difference. Depending on, again, how much does tuning make a difference? Essentially, the difference depends on the quality of your training data. And for training data which is not very good, the difference can be significant. My experience with reasonable training is about a factor of 5% at most. But still, you may be at 85 and you want to get to 90 to get your PhD and people will be happy. I mean, remember, the only thing you need to get a PhD is to satisfy a bunch of examinators sitting here which are going to make fun of you. So, no, and I was telling Andrea on lunchtime, this is showing how our universities are still stuck in the Middle Ages, because this has been exactly the same ritual ever since the Middle Ages, right? It doesn't change a bit. The student comes, defends his thesis, you know. Einstein did it, Kant did it, you know. Schrödinger did it. You're going to do it too. So this is very ritualistic. With that, we can try to get to the same thing now as image classifications for data cubes. And now we're going to do something different for a change. Okay? And when you open your image classification for data cubes, Kaggle, And when you click Edit, you're going to do something different. Now look at this right side at a button called Accelerator. Accelerator. Click here, and lo and behold, there's a GPU waiting for you. You didn't know there was a GPU there. Open a GPU for you.
Sorry, it's not in between the notebook options, so should we?
Not Notebook Options Accelerator. You don't have it? Did you get it? Why not? Are you logged in?
Are you
I'm sorry, I get it. I thought you would get. Have you edited first? You enter edit mode?
I see.
This one.
Huh?
Not on the GitHub, okay, this one.
Yeah.
No, I can't even see the notebook.
Because it's
No. Have you clicked the edit button?
no.
Okay, let me start again.
No, I mean, I don't get to that page at all.
No, I mean, you go image classification for data cubes.
Where is that? I don't find that.
Where are you? Oh, kaggle.com/essensing/code. Look here. Whoops, 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 too much. Okay, let's, come on, if you're not here, too big. Okay, if you're having trouble, this is the address. Hope that you find it.
Probably you need to get your phone verified in order to access it.
You need to get your phone verified. Yes, Kaggle wants to, I mean, how do you think you're paying for this? You're paying with your life.
Yeah,
Oh.
if it's just my life, then it's fine.
You pay, no, serious. You're paying with your life, I'm not kidding. So this is the address.
Souls?
Huh?
Kaggle does not accept the souls. I have to.
Oh, my soul, your life, yeah. It's Kaggle. I mean, this is like, no, it's tech, as my Google Yanis Varoufakis says, techno-feudalism. Okay, so hopefully now you should be able to get image classification for data cubes, and then you click Edit, and then you have a notebook option called Accelerator. Get it? Yes, no? Lorena, got it? Ah, okay, so you don't have it, so fair enough, but, okay, did you get it? I'm sorry?
Yeah.
Okay,
I have it, but she doesn't. Maybe.
Did you get your phone verified?
well, it's, fair enough. It's going to work if you don't have the accelerator, it's just going to take some time more.
You have to switch off others.
Huh?
No, you have to switch off the other session, other notebooks.
Yeah, you have to switch off other notebooks and so on. Yes. Okay. Okay. Whoops, too much. I did switched everything off. Okay, fair enough. Okay, edit. Okay, now the reason I'm going to switch on the accelerator, it will become clear in a little bit. Okay. Okay, can we continue? Okay, good. So you now have hopefully a notebook which hopefully is accelerated. and then you start again your notebook. This time you're going to get less CPUs than you would. Normally Kaggle gives you, I think, 6 CPUs. Now if you go to GPU mode, you get only 2, but you get a GPU, which for what we're going to do is a better deal. And then you install. Okay. And while it is running, okay, it's run for me. Now we're going to use a real data set. This is a bigger data set, not too big. It's one part of a Sentinel tile with band 2, 8, A, 11, and indexes NDVI, EVI, and NBR in an area of 1,200 by 1,200 pixels. But it's a tough area. So if you have managed to log in the system and install the bundle and run the library, you should be able now to create a data cube. So again, it's not creating from Amazon. I already pre-computed this cube from, it's actually, the original is Microsoft Sentinel 2A, but basically this data set is on a local machine. I've already created it and it's a local machine. And you should plot it. So, okay, so you see this one. It's a tough area. It's a tough area because it's a non-obvious area for, and you can see if just looking at the image, the colors are not enough to explain what's going on, because you clearly have here areas which are shown in sort of reddish, light red or pink. They are deforested areas. But these pink areas near the river, they're not deforested areas. They are wetlands. They are both areas. And also these areas here, which are on this side, they are also deforested. They are areas which are flooded during the year. It's a very tough area to classify, and Global Forest Watch gets it completely wrong. Now, we're also going to use a real sample. This is like a sample which has been carefully collected by a team of experts. So it's a very trusted sample. And this is a work that I'm conducting, and these are 3 postdocs and 1 senior researcher. And we've been working on this area for about a year. But this is a tough one. And this is what you get. These are the samples. Clear cut with bare soil, clear cut with burned area fires, clear cut with some vegetation, forest. I'm not going to explain a little bit, but mountainside forest, riparian forest, seasonally flooded, water, and wetland. Now, one thing which we like to do a lot, and I advise you also to do if you can, even if your data comes from another source, is to show the patterns. So if you click here, you're going to see some nice graphs. And what I've done is in the first line, I've selected the 3 indexes, NDVI, EVI, and NBR. And then I did something which might mystify to you, SITS patterns. Okay, what is this? This is actually a generalized addictive model, GAM, which is computed on top of the time series so that it gives you the variation of the data. It's a very good technique to understand your data. I'm going to go show it here, which is easy. I use the trick which I've learned. Now can you see it? It's a very good thing to do when you're dealing with time series. Okay, what is this? This is a mathematical approximation of the time series. Here we have 3 bands. And can you see what, okay, tell me, what can you see in this data set? Oh, wait. Red is EVI, green is natural burn ratio, and blue is NDVI. So what you're seeing here?
Spectral signatures?
Yes, spectral signatures. What do the spectral signatures tell you? No, it's not a classification. These are the training sets. This is the mathematical approximation. So this basically, for example, for clear-cut bare soil. Let's go back a little bit so you can understand. Remember that you had 944 time series of clear-cut bare soil, 983 samples of clear-cut burned area, and so on. What I've done here is I've taken the 940 whatever, and I've done here three mathematical approximations using a generalized additive model. One approximation for the NBR, one approximation for the NDVI, and one approximation for the NB. So it tells you how the data, it's a synthesized sense of the data. Typical profile approximated mathematically nicely. Remember that sometimes you don't have to be right. You just have to be fuzzy enough talking about things, especially when you use, I mean, it always works. When you use some statistically sophisticated terms to the computer guys who work on Python, it works like a charm because they have no clue what you're talking about when you say generalized additive model. They never heard of Hassi and Sibigiani and the gurus of machine learning. Never mind. So it's good to impress, but it's also real good, really serious stuff, used by real statisticians. So what can you tell me about this data set? What do you see there? Come on, you have to see something. They don't look the same.
It's a seasonal change, like during the year.
Clear-cut bare soil.
You see, is there a difference between clear-cut and bare soil?
It seems so.
Right. No, it seems so, and the difference is a lot on the natural burn ratio, as would expect. The NBR is sensitive to burned area. That's what the theory says, and that's what the practice shows. And do you see a difference between clear-cut vegetation forest? It's subtle, but it is. There is a difference. And you don't see too much the difference between riparian forest and forest, but there is there. But the most important one here, also the second most important one, is the difference between forest and seasonally flooded.
And the seasonally flooded and the wetland.
And the seasonally flooded and the wetland.
It really separates it.
Right.
I mean the curve of the green, which is the
But remember, what would happen if we had not put the seasonally flooded class? Now you know enough, you've been with me for about so many hours that you should be able to provide a response. Question: what would happen if I take out all the samples from the seasonally flooded forest?
I'm probably confusing all those pixels that fall into that category with something else.
With something else, namely? No, what's the closest one? What's you? No? Clear-cut vegetation. Clear-cut.
How is that the closest one? So how do you quantify which one of them are the closest to each other?
I don't do anything. What does is random forest or the PSDAE or TIP. That's, you know,
Okay. Yeah,
okay.
fine.
Okay, no, because it's a very good question from, in astrophysics, a lot of what you do and your life depends on explainability, right? You have to, for example, derive the laws like Hawking and Penrose from black holes, and everything boils down to explainability and validation of that explainability laws, right? In machine learning, you know who knows what Vapnik is? Anyone have heard of Vapnik? Who's Vapnik? The guy who invented support vector machines. So what Vapnik says, if you are on the machine learning world, you have to give up explainability for predictability. Give all hope of laws. Do you have any idea how ChatGPT works?
Generally, yes.
Yes?
But I cannot.
No, no, no. I don't think even the guys who devised it have any idea how it works. There's a nice explanation of that by Stephen Wolfram, the guy who did Mathematica, in his website about this. So, my point here, you're right, and it's very good that you are an astrophysicist. We need more astrophysicists in remote sensing. You're right. If I take this out, I'm going to put the classifier in trouble because it's going to try to find somewhere some box to put the classes. So it's, again, not obvious. And I'm telling you, when we started, we had 5 classes. Clear-cut bare soil, clear-cut burned air, clear-cut vegetation, forest, water. 5 classes. And then boom, 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 boom. And then we said, okay, what's missing? This, and this. Okay. So, yeah, go ahead. Yes, yes. Oh, I'm sorry.
Are these samples from a single year, or are these multiple?
No, the samples are from a single year.
Yeah, and when you train the model, how do you handle these interannual effects? Like you train.
No. We're doing step by step. Remember, what we're trying here, we have a benchmark, and the benchmark we have is visual interpretation, which has a 95% accuracy. And the current published in the literature is 82, 83%. We're trying to get to 90+% accuracy. No, we're not, this is real operational work, which is aimed to meet the EU deforestation-free goods law. So we're not, this is not academic work. This is like billions of.
But, do you also use like training model of a previous year?
No.
Like images from that particular year.
No, because we want, remember, we're doing here, this is an exercise of getting the absolute best model that state-of-the-art can devise. So our aim here is the absolute best model. So I'm not going to go into random forest. Well, I could do the random forest here, and you can get, but I don't have time. So in the interest of time, I'm going to give you a temp CNN model. And here it is. So I'm going to train the model, the samples with a temp CNN model. And hopefully this will run on the GPU, hopefully, to be faster. And there's a whole bunch of tuning that goes on, and I'm, on the interest of time, I'm sort of skipping that. And so here I'm taking the temp CNN, running on layers. While it is running, I just want to point out your attention to something that some of you may find interesting, and we didn't have time to do it today, which is object-based time series analysis. There's a notebook on that, which is on the Kaggle. I don't have time to cover it today, but I'm just telling you it's there. And again, it's basically the state of the art on this, and something else that you cannot do it in Google. And you cannot do it anywhere else, too, for that matter. I don't think anyone here on the building that does big data can do this. Really, I'm proud to say it's state of the art. I mean, other people do, but you can really not do it right now. Okay? So, again, the message here is what it is doing. If you want to do time series, remember the basics. Build your cubes, get your samples, train your models, classify. It's as simple as that. If you do your API, try to make a simple API. Don't make it more complicated than it needs to be. Keep it simple. So let's wait. I think we have some little bit of minutes so we can finish this. If you really have to go, I'll show you the result, because the result is here somewhere. And by the way, one important bit here, which I didn't mention, is the sits classify function works for any size data. If the data is on the CPU, it parallelizes everything of how many virtual cores you have. You don't have to set up desk or whatever, XArray and desk. It does everything for you. It breaks the image. It Googleizes. Basically, essentially, what we're doing we're doing here at Google. Yeah, go ahead.
Regarding this, I have a little bit of a technical question.
Yes.
Just
go ahead.
What is there any I don't know, tips and tricks with regarding the memory management while working with the data cubes? Is there something specific, or just there's the standard premise: don't load into memory something that doesn't fit there?
Don't load into memory something that doesn't fit there. But remember the following, okay? But there's more to it. First thing is, if you have a reasonable machine, in these days, a reasonable machine is something like 64 cores and 512 gigabytes of memory. What the system does, it first of all takes advantage of the fact that now the images come as COGs, which is cloud-oriented geotiffs, normally breaking by this. So it breaks the images. Machine 1 get this, machine 2 get, this is Google, right? Yeah. This is the equivalent of Google on the fly. And then you send bits and pieces to the machines, get there, and you do it. That's when you have the CPU. When you have the GPU, it's different. It looks at the size of the GPU memory and optimizing the load to fit the memory of the GPU. So it's always trying to fill as much GPU memory as possible. So fill the GPU memory, process, go back. Fill the GPU memory, process, go back. It's different because the GPU has one memory, so you have to load as much as you can, but not more than the memory. So you still have to be careful with how you load, but you load into GPU and then bang, back. Load into GPU, bang. So the two alternatives. If you have CPUs, use your virtual machines like Google. If you have GPUs, use as much as you can the GPU. And that's how it works. So, okay, so it has built the model. And then I'm going to classify, and if I'm correct, this should be fast if my GPU is running and if I did my code right. should not be too fast. So what it's doing now, it's saying, okay, I'm pushing as much as I can to the GPU memory. I'm reading the data, pushing it to GPU memory, classifying, getting back. In this case, it's pushing everything to the GPU memory because there's less than 16 gigabytes of data. So now the time here is actually I/O. It's not real the classification. It's basically the time that it takes to read from whatever disk is there on Kaggle and read it, because the memory is instantaneous. I mean, so if you, and what we're doing is we're getting large data, we're getting the same time we get in like 12 CPUs with random forest with 1 GPU with deep learning. So the times are the same. And they're essentially, so if you have, so the only problem if you have CPUs and try to do deep learning, it becomes very slow. You can run it, okay, but it's slow. So, but that's what everybody would tell you. Okay, I think while waiting for the end of today, I have to finish by asking you if you have any general observations about what we learned today and what we discussed today, and whether it met your expectation, since you're brave enough to stay for, what, 4.5 hours, which is a lot of time for a tutorial. So thank you for your, appreciate you being here. Any points, questions, issues you like to raise? Silence is not always good.
I just have one question.
Yes.
About this application. Here we are training a CNN model using as ground truth single pixels, right? Not a full image classified.
Oh, I'm using as not single pixels, single time series. Okay, but yeah, go ahead.
So you have a list of pixels with their time series classified.
Yes.
So you don't have the full image that you are trying to.
No, but that no one has it.
Okay.
You don't train on a full image. You train on samples.
Yeah. Okay.
I mean, that's how I learned remote sensing.
No, because in my case study,
It's a supervised classification model. It's a so-called supervised classification
No,
model.
because in my application, I have a different type of ground truth where I have I'm splitting the full image in smaller patches.
but who has a full image classified? But if you have the full image classified, why do you need to do the classification?
To apply the model in other records.
Sometimes you have absolutely, you have the information hidden in some like features of the image, like.
No, wait.
when you
Information
classify
hidden on.
cats and dogs, you don't classify them.
No,
single
okay.
image.
Fair enough.
So that's why.
No. I mean, this is not the normal case I've came across.
Yeah, I mean, it's different approaches. So here, with the data available in the EU, we usually run random forest classification on entire population. Imagine, for example, that we have oil agriculture parcels declaration.
Mm-hmm.
And then if there is a mask on it, so we know where you find arable land, that's remain on that one because that's the easiest, more trivial case.
Right.
So we have the declared crop, or the farmers declares the crop, so we have an assumption, or a pre-assumption what's on the crop.
Okay.
And then random forest is basically looking for the outliers values and looking for
But why do you use
set of pixels.
why do
that
you use
doesn't
random
belong to
forest for an outlier? That's what.
Yeah, that's a question. And I mean, my personal opinion that the random forest is not the best model for that. Maybe the easiest to run.
And the problem I have with those kind of ground truth is that in my case I have only one ground truth for the full year.
Yes.
So it's not a
Yeah, but
ground
that's
truth
not a
for
ground
every-
truth.
for
So
every
this is
unit.
what we misunderstood in a classical way of thinking.
It's not a
A
real
real
ground
ground
truth,
truth
it's
is
an
the training data like he's talking about, that it's really somebody went there and proved that this is winter wheat and that's solar wheat.
Okay. So essentially, what I
Our
am
way of thinking in this is
I don't want to keep you past the hour, so I'm showing you what the result looks like, which is a temp CNN classification, which mostly gets very good. I mean, you have to believe me that the temp CNN classification is not the best, but I mean, it's very close to a very good classification. I'm running this on Kaggle, but it's sometimes for this reason, it's taking me more time than I should. And I think if anyone wants to stay with some more questions, but I'm most grateful for your presence here. And I hope that if you have any doubts later on, we can communicate, and appreciate you being here. So please, if you want to leave or you want to stay, again, I would appreciate any feedback you might have. Any other comments? Or I'm sorry to this. I mean, Europe. I mean, my point here is the following: if you have polygons, okay, with labeled, you still need. And if I understand a little bit about European data, your problem is not of lack of data, but too much data. Because you need to make sure that you're feeding, because in this case, what happened is people have taken a long time to select good samples. Now, you're deluged with samples, right? Because if you have a Lucas map or some map, you have lots of polygons with samples there, right?
Yeah, we have the full map of a given area classified.
Right.
This is still for only the cultivation that the farmer declares at the end of the growth period.
Right.
So we don't have the what's in the territory at each timestamp.
Yeah, but what I mean is that your problem is too much data, not too little.
Yeah.
And then you have to resort to other kind of things.
Yeah, exactly. So
And
here
then,
you
no. I would then, there's a different part of the book which talks about improving the quality of training samples. And we did a lot of work on this. I don't have time to do it, but there is a huge discussion here on how to clean samples, how to create, and we use self-organized maps to clean up data sets which are inconsistent and so on.
And do you also have the training test misclassification matrix?
Oh yes, that's everybody does, right?
Yeah, okay.
A k-fold validate, but that's the obvious.
Yeah, I see.
What I'm saying is that when you have, in this case, we had 50,000 samples. And basically what we're doing is we're trying to clean which samples are good, which samples are bad. And we have techniques for that. These are not the only techniques, but in your case, I would advise you not to blindly pick up what comes out of Lucas or these data from Europe and just clean them first. Make an effort to clean them, make an effort to select just the best samples. Some of these techniques here with self-organized maps might be okay. Okay, so I'm not going to show off. Let's see. So it will. Oh. No, come on. Why is this? There's some errors here. Okay. So. No, it's just that you get you test, now it's classified, then you smooth, then you classify, then you plot, then you get something out. In this case, a very good data set. So I think hopefully the message here is, if you want to use time series, you need to organize your data so the architecture allows you to extract your data sets. So you need a representation from your samples, you need a representation for your cube, and you need for your models to read this kind of thing. If you use Python, and if you want to use Python models with time series, even if you never used and you know where to start, one thing that you could try, it's since everything here is on Torch, the ways to do this on R are very similar to the ways to do this on Python. Because essentially the Torch library, here is just the samples, then for example, if you look at this Torch pixel spatial encoder, Andrea might recognize this, and then this actually is very similar to the code that was done in Python, and therefore you might get some ideas out of it. Torch multilinear batch renum liu, so okay, and then it goes. So you might want to get something out of it if you need. But that's, I mean, or of course you go do directly in Python. Other alternative, you can use sets to organize the data for you and process everything in Python. Now that you know what the data is, just, it saves you the time of organizing data, of producing the samples and so on, but you still have your Python environment to work on. Because it's, in the end, it's all metadata that talks about files, so there's nothing miraculous there. And so you can even, if you read the metadata, you can put into Python. It's just that because many of these algorithms that come into Python have strange ways by which the input data is organized, and which are, I would argue, not very good. Oops.
Professor, is wildfire assessment a good?
I'm sorry?
Is wildfire assessment a good application for this?
Which one?
Wildfire.
Well, yeah, I mean, in principle, yes, because there's nothing, again, I'm careful now.
Or would it be an overestimation with applying this model for wildfires?
Why? I mean, the point here is you need, for as in any case, a number of samples and classes good enough that you detect. Again, remember, what we're talking about here is either, in your case, you don't know where the wildfires are. So you have to ask yourself the following question. What else is there? What else is there? If it's not wildfire, what is it? Is it a pasture? Is it a forest? Is it a small bush? What's there? Because the classifier is stupid. If you don't run out the possibilities, it will give you a wrong answer. The trick here is to be smart, ecologically speaking, and develop classes which cover the spectrum of possibilities of the classifier. Now, the classifier is like, you know, it will try to come up with something. So your trick is, okay, I have wildfires. What else is there? What if it's not a wildfire? What is it going to be? Oh, it's got to be A, B, or C, or D. Okay, then A, B, C, or D. And wildfires. In this example, effectively, this, for example, we want to get burned areas and separate from clear cuts. So here, typically, you have the NBR, which is very good at the temporal variation of the NBR. Not the NBR itself, but the fact that the NBR does this when you have a fire. But if this is the only class you train, that's the only class you get. So you need a lot of other classes. Otherwise, you know, that's the hard thing. Something which is obvious to humans is not obvious to the classifier. And the other thing is the variations, the natural variations in nature are mind-boggling. Nature has evolved over. So it's our words sometimes fail to to represent what nature has. So that's the trick. I mean, the two issues. One is learning how to use time series, which I hope I've given you the hints of where to go. The other is after you now know how to climb the stairs, to know which door to open. Yeah, go ahead.
Have you tested the principal component analysis method?
Let's let the guys leave. This is, well, not the, I mean, well, why? Okay, I mean, okay, principal components is a different story.
It's a different story.
No, what's the logic of principal components? The logic of principal components used to be when you didn't have enough bandwidth or enough computing to represent the full set of classes. And then you use the principal components of lens.
Find out which one represents the best.
Why, but if you have all the data, use all the data. My question is, if you can have, my point is simple. If you can have 10 sentinel bands, why should you use 3 principal components? Give me a good reason.
Yeah, it's true. So 20 years ago, we did to reduce the calculation.
No longer.
And now we don't need to do that.
Right. So I hope that if you got something out of it, and I am happy very much. Thank you for your presence and anything. And by the way, okay, if you want a copy of the slides,
Please.
could you be so kind as to send me an email? And how do you find my email? Okay, good question.
It was in your email.
Yeah.
Right, that's a good question. So you now have the answer.
The same email we are reading every new lecture.
May I have one last question?
Yes, of course.
If I would like to test your things for Hungary, do you recommend it to do it on the AWS or go to the Microsoft cloud? Which one is the last one you know how to say?
The cheaper one.
No, the cheaper, I mean, the
No,
cheap.
we thought
Yeah.
it's, you don't pay for it now, do you?
Until you don't do analysis on the data,
No,
no?
are you basically, let me get you one thing. Are you like working for the whole of Hungary? So simple question, how many tiles of Sentinel are we talking about?
The whole of Hungary is like 4 strips. 12, I think. 12
Come on.
Sentinel 2 or 14, because they have to shape.
Oh, how much data is that?
I think one,
Yes.
just, it's one.
Right, does it fit here?
No,
It does?
or likely, I mean,
If you're
1.2
speaking 1 image per tile,
1.2 terabytes per one
Yeah.
cover about
Yeah,
the 4 bundles, 5 bundles.
no, the 1.2 terabytes per year.
No, per coverage.
No,
No, per year? No.
no, come on,
what the coverage
some calculations.
should be.
Oh, let's do some calculations here. Back of the envelope, okay?
Yeah.
So, okay, you have, simple, 5,000 plus 5,000 plus 14 tiles
Yeah.
times 14 tiles.
Oh, yeah. 5,000 times 5,000.
Yeah.
Yeah.
Yes.
Yeah.
Oh, because it's a plus, I'm sorry.
Times 24 per year, okay?
Yeah.
12 bands, times 8 bits,
8 bits.
times 10 bands, okay?
Okay.
14 tiles, 24 instances, 8 bits, 10 bits, divided by 1x minus 9,
Okay.
672 gigabytes.
Gigabytes.
You don't have enough terabyte fits here.
Okay, he has a Mac, I just have a crap.
No, let me put it this way. No, let me put it this way. It pays that you pick up a server on your machine at the lab and download the data and leave it for 2 days to regularize the data and have the data regular there on Hungary and don't have to pay anyone anything, and then you 660.
Then I download it.
No,
data.
you do as follows, okay? Let me show the code. It's as simple as that. You say, well, we did this all the time, so.
Yeah.
Okay, now I show you. You do the following. You say, I mean, it's 2 comments. Where is it? Yeah, like this. You say Microsoft Planetary Computing, Sentinel-2A, and put the whole tiles of Hungary there, and put a start date and date, all the bands, and okay, you have the cube, okay? And then you say regularize, and find a place on your lab that has 600 and a terabytes of space, and plum, 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 and you know, wait for the weekend, go for a nice Tokai and listen to Ligeti, and you're done. You don't like Ligeti. You don't like Ligeti, right? Or sing the Kodai songs or whatever. Okay? So just do it. And in the morning of Monday, you should have your data, and then you just save it in another disk just to make sure. And you spread around Hungary, and you're going to be famous because you're spreading out the data cubes for Hungary. And then you're done. You don't need anything else. And then you do it on your own machine, and how about boom? It's as simple as that.
What is the benefit of downloading them from Microsoft or Amazon versus just going to ESA to the...
It's faster.
It's
simple.
faster.
No, first of all, ESA doesn't have a stack. So you cannot query ESA. You cannot do this.
That is true. You just have to go to the online platform, to the archive.
Yeah, well, it's a pain. You don't do this, right? You want to do this. You want to specify your area? Oh yeah, my suggestion is build a regular data cube. That's all you need for Hungary for say 15 days or something, and start working. And then you figure out if you need something else.
Regularization is performed on in cloud or locally when you run it in
No, it depends on which machine. Bye, Valena. It depends on which machine. If I run here, okay, if I run this code here, it's performed on my machine.
Yeah, but okay, if I run it on Kaggle, it's performed on the
Kaggle, yes, but it runs locally on Kaggle, so you don't get it to yourself. But if you run this on your machine in Croatia.
So regularization is done on the machine, but the data is originally in cloud.
The original in the cloud, so you read. But you do it step by step. So you don't download all of the data at the same time. You could, but that's easier. I mean, this takes some time, but in 2 or 3 days you'll be doing Croatia, you're doing Hungary. I mean, come on.
So we download the regularized cube data and then
No, you build the There's no regularized cube data on Microsoft.
No, but we build it.
Yes.
It stays in the cloud.
No, doesn't stay in the cloud.
Doesn't stay. It already downloads to my PC.
Yeah.
Got it. And from there, all the rest, like any machine learning, blah blah, is run on our machine.
Yes.
Okay. And this is as a client server local.
Yeah, I mean, whatever. Nowadays it's okay. So we're now running to the next session.